So, here's something worth sitting with tonight. Right now, wherever you are, you're being deceived. Not by anyone in particular, not by a screen or a headline or a person trying to sell you something. You're being deceived by the most ancient and most persistent liar in the universe. Light. That blue sky you saw today? It was never blue. The sky has no color. What you saw was a trick, a consequence of tiny gas molecules scattering short wavelengths more than long ones, painting a false ceiling across the atmosphere that doesn't actually exist as a surface at all. The mirror in your bathroom this morning, the one that showed you your own face, it flipped you. Left became right, right became left, and the person staring back at you was a reversed copy that nobody else in the world has ever seen, because everyone who looks at you sees the unreversed version. You've never actually seen your own face the way other people see it. And that shimmering puddle of water you might have noticed on a hot stretch of highway last summer, the one that vanished as you drove closer. There was no water. There was never any water. What you saw was a patch of sky, bent and displaced by layers of superheated air hovering just above the asphalt, folded downward into your eyes through a trick of refraction so convincing that your brain simply decided it must be a reflection off a wet surface. Light lied to you, and your brain believed it without question. These aren't rare or exotic phenomena. They're everywhere. They're constant. The shimmering iridescence on a soap bubble. The rainbow that appears after a storm and vanishes if you try to walk toward it. The way a swimming pool looks shallower than it really is. The reason a spoon appears to snap in half when you dip it into a glass of water. All of these are lies. Optical deceptions that light performs effortlessly, automatically, every second of every day, without anyone asking it to. And here's what makes all of this so much more interesting than just a list of tricks. Every single one of these deceptions, once someone figured out how it actually worked, became a technology. The same bending of light that produces a mirage on a highway is the exact physical principle that traps a beam of light inside a glass fiber and carries your internet traffic under the Atlantic Ocean. The same thin film interference that makes a soap bubble shimmer with color is the same physics that coats every camera lens, every pair of glasses, every telescope mirror on Earth with invisible layers designed to eliminate unwanted reflections. The same scattering that makes the sky blue is what lets doctors peer inside your body with fiber optic endoscopes, and what tells astronomers the chemical composition of a star 10 billion light years away. Every lie became a tool. Every trick became a technology. Every deception, once understood, was turned around and used against light itself. So here's what I want to sit with tonight, and I think these questions matter because they're not abstract. They're about you, about what's happening in this room, right now, between the light in your eyes and your brain. Why is everything you're seeing right now, these walls, these colors, the darkness beyond the window, constructed from distortions that your brain doesn't even know it's correcting for? What would you actually see if your visual system showed you the raw, unprocessed truth? How did the same bending of light that creates a phantom puddle on a hot highway end up carrying the text message you sent an hour ago underneath the Atlantic Ocean? How did colors on a soap bubble lead to the coatings on every camera lens and telescope mirror on Earth? How does the same physics keep showing up, again and again, first as a trick and then as a tool? And who were the people who cracked these deceptions? Who looked at a rainbow and didn't just admire it but pulled it apart, angle by angle, wavelength by wavelength, until the beauty was explained, and the explanation was even more beautiful than the phenomenon itself. These are the questions, and the answers, I think, tell one of the most satisfying stories in all of science. Because it turns out that every lie light tells, once you understand the mechanism, becomes a technology. Every trick becomes a tool. Every deception, decoded, gives you power over the thing that deceived you. We're going to go slowly. There's no rush at all. And if you drift off somewhere along the way, that's perfectly fine. The light will still be doing its tricks in the morning. But if you stay with me, I think you'll find that what seems like a simple story about illusions is actually one of the most satisfying stories in all of science. Because it connects the simplest thing you can observe, a shimmer of color on a puddle, to the deepest physics we know. And the people who made those connections were some of the most brilliant, stubborn, and occasionally very lucky human beings who ever lived. Let's start with the oldest and most dramatic lie that light tells. The one that has been fooling travelers in deserts for thousands of years. The mirage. Imagine you're walking across a flat, sun-baked expanse of sand. The air is hot, the horizon shimmers, and up ahead, maybe half a kilometer away, you see what looks unmistakably like a pool of water. It's shining. It has the characteristic silvery gloss of a wet surface. You can even see what appear to be reflections in it. Maybe the faint image of a distant rock or a tree, upside down, just like you'd see reflected in an actual lake. Everything about it screams water. You walk toward it, and as you get closer, it recedes. It's always the same distance ahead, always just out of reach, always shimmering and beckoning and promising something it can never deliver. Eventually, if you keep walking, it disappears entirely, and behind you, if you turn around, there's another one, shimmering in the direction you just came from. This has been happening to people for as long as people have walked through hot landscapes. Herodotus mentioned it. Medieval travelers in the Sahara wrote about it. Soldiers in every desert campaign from Alexander's armies to the Gulf War have seen phantom lakes that weren't there.
And for most of that history, the explanation was either supernatural, a curse of the desert spirits, or psychological, a hallucination produced by heat and thirst and desperation. But a mirage is neither of those things. A mirage is real. You can photograph it, you can film it. A camera with no brain, no thirst, no expectations, will record the same shimmering pool that your eyes see. Whatever is happening, it's happening to the light itself, not to your mind. The light is genuinely arriving at your eyes from a direction that makes it look like there's water on the ground. The question is why? And the answer begins with something you already know, but might not have thought about carefully. Light travels in straight lines. That's one of the oldest observations in optics, dating back to Ibn al-Haytham's experiments with pinhole cameras over 1,000 years ago. Light from a candle, passing through a small hole, hits the opposite wall in a predictable spot. The geometry is rigid and clean. Straight lines, sharp shadows, no surprises. But that principle, light travels in straight lines, turns out to be a simplification, a useful one, and one that works brilliantly in most everyday situations. But it breaks down when light passes through a medium whose properties change from one place to another. And in the atmosphere above a sun-baked road, the properties of air change dramatically with height. Here's what's happening. The sun heats the asphalt or the sand, and the asphalt heats the thin layer of air directly above it. Hot air is less dense than cool air. That's basic thermodynamics. So right above the road surface,
you have a layer of air that's significantly less dense than the air a meter or two higher up. And here's the key fact, the one that makes the whole trick work. The speed of light in air depends on the air's density. Denser air slows light down very slightly. Less dense air lets it travel very slightly faster. The difference is tiny. We're talking about changes in the speed of light of maybe a few parts per million. In your everyday experience, you'd never notice. But light, traveling over a long horizontal distance through these layers of air with gradually changing density, does notice. Because when one side of a wavefront of light is traveling through slightly faster air than the other side, the wavefront bends. Gradually, continuously, curving away from the hotter, less dense air and toward the cooler, denser air above. This bending is called refraction, and people had been puzzling over it for a very long time before anyone got the math right. Ibn al-Haytham, writing around the year 1011, studied refraction carefully. He knew that light bends when it passes from air into water or glass. He measured angles. He tried to find the relationship between the angle going in and the angle coming out. But he couldn't crack the formula. The relationship isn't a simple proportion between the angles themselves. It's a proportion between the signs of the angles, and that's a subtlety that eluded some of the sharpest minds in optics for 600 years. The person who finally got it right was a Dutch astronomer named Willebrord Snellius, working around 1621. Snell's law, as it's universally called now, says that when light crosses a boundary between two materials, the sine of the angle of incidence divided by the sine of the angle of refraction equals a constant, the ratio of the speeds of light in the two media. That constant is what we call the refractive index. It's elegant, it's precise, and it governs everything from the focusing power of a lens to the bending of light in the atmosphere. Every optical designer, every lens grinder, every fiber engineer works with Snell's law as their most basic tool. Snellius himself never published the law. His result was found in his unpublished manuscripts after his death. René Descartes independently derived the same law and published it in 1637 in his Dioptrique, as part of the same body of work where he analyzed the rainbow. There's been some historical debate about whether Descartes knew of Snell's work, but the consensus is that both discoveries were genuinely independent. The law is called Snell's law in the English-speaking world and the law of Descartes in France, which feels about right for a scientific priority dispute. The essential idea is simple enough, though. When light moves from a faster region to a slower one, it bends toward the boundary, steepening its angle. When it moves from a slower region to a faster one, it bends away from the boundary, flattening out. And there's a deeper principle underlying Snell's law, one that the French mathematician Pierre de Fermat articulated in the 1660s. Fermat's principle says that light always takes the path that minimizes the travel time between 2 points. In a uniform medium, that's a straight line. But when light has to cross a boundary between a fast medium and a slow medium, the fastest path isn't a straight line. It's a bent path, one that spends more distance in the fast medium and less in the slow one. The same way a lifeguard running along a beach to reach a drowning swimmer would angle their path to spend more time on the sand, where they're fast, and less in the water, where they're slow. Snell's law falls out of Fermat's principle automatically. The geometry of minimizing travel time produces exactly the relationship between angles and refractive indices that Snell described. In the air above a hot road, the light from the sky is traveling downward at a shallow angle. As it descends, it enters hotter and less dense layers of air, where it can travel slightly faster. So it bends, it curves. And if the temperature gradient is steep enough, the light curves so much that it actually turns around and heads back upward, reaching your eyes from below, from the direction of the road surface. Your brain receives light that appears to be coming from the ground, and here's what makes the deception so convincing. The light really is an image of the sky. It's blue because it is skylight that has been bent downward. If there are clouds above, you'll see them reflected in the phantom puddle. If a distant object is near the horizon, you might see a shimmering, inverted image of it below the mirage, just as you would in a real reflection off a real body of water. Every detail that your brain associates with a wet surface is present. The brightness, the blue tint, the reflections, the shimmer caused by slight variations in the atmospheric temperature gradient, creating ripples in the image. Your brain, which has spent your entire life learning that light coming from below a horizontal surface usually means a reflection off a wet surface, does the only thing it knows how to do. It interprets that light as a reflection. It sees water. It sees a puddle. It constructs the illusion of a shimmering lake, because that's the most sensible explanation your visual system can come up with for light arriving from that direction with that quality. And the shimmer itself, that flickering, unstable quality of the mirage, arises because the temperature gradient above the hot surface isn't steady. Convection cells form and dissolve. Pockets of hot air rise, pockets of cooler air sink. The refractive index of the air fluctuates, and the refracted light path shifts and wavers, producing the characteristic heat shimmer that you see above any hot surface, be it a desert, a sun-baked road, or the top of a barbecue grill.
Photographers and snipers know this shimmer as heat haze, and it degrades the sharpness of any image viewed through it. The same turbulence that creates the mirage also limits how clearly you can see through the atmosphere, a problem that will become central to our story when we get to telescopes and adaptive optics later. The mirage is real in the sense that the light really is there. It really is arriving at your eyes from below. The deception is in the interpretation. The light has been bent by the atmosphere, and your brain has been tricked into reading that bent path as a reflection. And here's what's elegant about this. The physics of the mirage, refraction through a medium with a gradient in its optical properties, turns out to be exactly the same physics that makes lenses work, that makes optical fibers carry data, that makes your eye focus an image onto your retina. The mirage is nature performing the same trick that every optical engineer exploits every day. The only difference is that nature is doing it with air instead of glass. Now, there's a particular version of this bending that matters enormously for the rest of our story, and it happens when the bending becomes so extreme that the light doesn't just curve, it reflects. Total internal reflection, it's called. And to understand it, we need to think about what happens when light hits a boundary between two materials at a very shallow angle. Imagine a beam of light traveling through glass, heading toward the surface where the glass meets air. Glass is denser than air, optically speaking. Light travels slower in glass than in air. So when the light reaches that boundary, Snell's law tells us it will bend away from the surface, spreading out into the air at a steeper angle. But here's the thing. If the light hits the boundary at a shallow enough angle, the math of Snell's law demands that the refracted beam would have to bend away at an angle greater than 90 degrees. And 90 degrees is the surface itself. There's no physical way for the light to exit. It can't bend past the surface. So instead of passing through, it bounces completely. Every photon reflects back into the glass, as if the surface were a perfect mirror. And it is a perfect mirror in that moment. Better than any silvered surface you could manufacture. A silver mirror reflects maybe 95% of the light that hits it and absorbs the rest. Total internal reflection wastes almost no light. The reflection is essentially 100% efficient. Every photon bounces back. Nothing is absorbed. Nothing is transmitted. The boundary between the two materials becomes a perfect, lossless reflector. And here's a detail that has practical consequences. The critical angle, the shallowest angle at which total internal reflection occurs, depends on the ratio of the refractive indices of the two materials.
A higher ratio means a smaller critical angle, which means that total internal reflection happens for a wider range of angles, which means that light gets trapped more easily. That's why diamonds sparkle the way they do. Diamond has a very high refractive index, which means the critical angle for total internal reflection is very small, which means that light bouncing around inside a diamond hits many surfaces at shallow enough angles to be totally reflected. The light gets trapped, bouncing and bouncing inside the stone, and each bounce sends a flash of brilliance toward your eye. And here's where the mirage connects to something much larger. Total internal reflection is the same phenomenon that traps light inside an optical fiber, a thin strand of glass with a core that has a slightly higher refractive index than its outer cladding.
Light enters one end, hits the core cladding boundary at a shallow angle, totally reflects, hits the other side, totally reflects again, and zigzags its way down the length of the fiber, trapped, contained, guided, for kilometers without escaping. The mirage on a desert highway and the fiber optic cable carrying your video call underneath the Pacific Ocean are consequences of the same physical law. A trick of light in the desert became the backbone of global telecommunications. We'll come back to that story later, because the history of how we learn to trap light in glass is one of the most satisfying engineering tales of the 20th century. But first, I want to stay with deceptions for a while longer, because the mirage is just one of many lies that light tells. And the next one, the one we're about to talk about, might be the most beautiful lie of all. You've seen it. Everyone has. Usually after a rainstorm, when the sun comes out and the air is still thick with tiny water droplets, a great arc of colour stretches across the sky. Red on the outside, then orange, yellow, green, blue, and violet on the inside. Sometimes, if you're lucky, there's a second, fainter arc above the first, with the colours reversed. A rainbow. And the strange thing about a rainbow, the thing that makes it fundamentally different from almost any other visual phenomenon, is that it isn't actually there. You can never reach a rainbow. You can never stand beneath one. You can never find the pot of gold at its end. And not just because the gold is a myth, but because the end is a myth too. The rainbow has no location. It exists only in the geometry between you, the sun, and the rain. Move, and the rainbow moves with you. Two people standing 50 meters apart see two different rainbows, each one centered on their own personal line of sight. A rainbow is, in the most literal sense, a private optical illusion, custom built for each observer by the combined accident of sunlight and water. And the story of how we figured that out starts in a most unlikely place, with a French philosopher, a closed room, and a very large glass sphere. The rainbow must have seemed genuinely magical for most of human history. It appears from nothing, hangs in the sky as an enormous arc of impossible colour, and then fades away as if it were never there. In the book of Genesis, God sets a rainbow in the clouds as a sign of his covenant with Noah. In Norse mythology, the rainbow is Bifrost, a burning bridge connecting the world of humans to the realm of the gods. The ancient Greeks considered it the path of the messenger goddess Iris. Cultures around the world, separated by oceans and millennia, all looked at the rainbow and saw something divine. And yet, the rainbow is physics, every bit of it.
The colours, the arc, the way it appears only when the sun is behind you and rain is in front of you. The faint secondary bow above, with its reversed colours. All of it follows from one simple fact. Sunlight enters a raindrop, bends, reflects off the back surface, bends again as it exits, and in the process, different colours bend by different amounts. That's the entire explanation, and the man who first worked it out in mathematical detail was René Descartes in 1637. Descartes is famous for many things. I think, therefore I am, the Cartesian coordinate system, the mind-body problem. But tucked into one of his less well-known works, a treatise called Les Météores, published as an appendix to his Discourse on the Method, is a remarkably careful geometric analysis of how light behaves inside a spherical water droplet. Here's what Descartes did. He imagined a ray of sunlight, a single beam of white light, hitting the surface of a perfectly spherical raindrop. At the surface, the light refracts, bending inward as it enters the denser medium of water. The light travels through the interior of the drop until it hits the far side. At that back surface, some of the light passes through and exits the drop, but some of it reflects, bouncing back toward the front of the drop. When this internally reflected light reaches the front surface again, it refracts once more as it exits back into the air. So the light enters, bends, bounces off the back, bends again as it leaves, and the total angle through which the light has been deflected, the angle between the incoming sunlight and the outgoing ray that reaches your eye, depends on where on the drop surface the light enters. A ray hitting the very centre of the drop bounces straight back. A ray hitting the edge barely enters at all. And for rays hitting everywhere in between, the deflection angle varies. But here's the crucial thing that Descartes discovered by tracing these rays carefully through the geometry. The deflection angle doesn't change uniformly. As you move from center to edge, the angle changes slowly at first, reaches a maximum, and then starts changing rapidly. The result is that a huge number of rays entering the drop at slightly different points all come out at nearly the same angle. They pile up, they concentrate, and that concentration angle, the one where the most light accumulates, is about 42 degrees from the line connecting the sun to your head's shadow on the ground. That's why the rainbow is an arc. You see it at 42 degrees from the anti-solar point, the point directly opposite the sun from your perspective. Every raindrop in the sky that happens to be at exactly 42 degrees from that line sends concentrated light to your eyes. Drops above that angle send light over your head. Drops below it send light at your feet.
Only the ones right at that critical angle contribute to the rainbow you see. And because all directions at 42 degrees from a central point form a circle, or rather a cone, you see an arc, a portion of a circle, with you at the center. Descartes worked all of this out with pure geometry, tracing ray after ray through his theoretical raindrop, computing angles with careful precision. The method he used was essentially what we'd now call ray tracing, following individual beams of light through the geometry of the drop, applying Snell's law at each surface, computing the deflection, and then asking, at what angle do the emerging rays pile up? He reportedly traced hundreds of individual rays, each entering the drop at a slightly different height, and tabulated the exit angles. The work was laborious, done by hand, with no computers and no calculators, just careful trigonometry and patience.
He even verified his calculations by building a large glass sphere filled with water, essentially a single enormous artificial raindrop, and shining light through it, measuring the angles at which concentrated light emerged. When the measurements matched his calculations, he knew he had found the right explanation. The agreement was excellent. The geometry was right. And there's a detail in Descartes' analysis that often gets overlooked, but is worth mentioning because it connects to a broader principle. The reason the rainbow appears at a specific angle, 42 degrees for red light, is that this is the angle of minimum deviation. It's the angle at which the exit direction of the light is least sensitive to changes in the entry position. Rays entering the drop slightly higher or lower than the optimal point all emerge at nearly the same angle. This bunching, this concentration of many rays at one angle, is what makes the rainbow bright enough to see.
It's the same mathematics that governs caustics, those bright curves of concentrated light you see at the bottom of a swimming pool on a sunny day, or the flickering bright bands on a wall when sunlight passes through a glass of water. In each case, rays converge and pile up at specific angles or positions, creating regions of unusually high intensity. The rainbow is a caustic of the atmosphere, drawn on the sky by the collective optics of billions of water droplets. But Descartes missed something. He could explain the shape of the rainbow, the arc, the angle, the way it appears opposite the sun. What he couldn't explain was the color. His analysis treated light as a single thing, a single beam that bends by a single amount. He had no way to account for the spectrum, for the fact that the rainbow isn't just a bright arc, but a bright arc separated into distinct bands of color. Red on the outside, violet on the inside.
That explanation required knowing something about light that Descartes didn't know, something that wouldn't be discovered for another 30 years by a young man sitting in a darkened room in Lincolnshire with a triangular piece of glass. Isaac Newton's prism experiment, performed around 1666 and published in detail in 1672, showed that white light is a composite. It's a mixture of all the colors of the spectrum, each of which bends by a slightly different amount when it passes through glass or, crucially, through water. Violet light bends the most, red light bends the least, and everything else falls in between, in the order you know by heart: red, orange, yellow, green, blue, violet. When you combine Descartes' geometry with Newton's discovery of dispersion, the rainbow finally makes complete sense. Sunlight enters a raindrop, and each color refracts by a slightly different amount. The red component bends less, so it exits the drop at a slightly different angle than the violet component. The concentrated ray angle that Descartes calculated is slightly different for each color. Red concentrates at about 42 degrees. Violet concentrates at about 40 degrees. The 2-degree difference between them is what separates the colors into distinct bands. Red ends up on the outside of the arc, violet on the inside, and every other color slots neatly in between. That's the rainbow. Geometry plus dispersion. Refraction plus reflection, plus the fact that white light is secretly a blend. And every single drop of rain contributes only one color to your eye. The drops at 42 degrees send you red. The drops at 40 degrees send you violet. The drops in between send you the intermediate colors. Your eye assembles them into a continuous arc, but each color is coming from a different set of drops.
The rainbow is a mosaic, composed by millions of individual droplets, each one contributing a single hue to the collective illusion. And about that secondary rainbow, the faint one sometimes visible above the primary. It exists because some light bounces inside the raindrop not once but twice before exiting. 2 internal reflections instead of 1. Each additional reflection is imperfect, so each bounce loses some light, which is why the secondary bow is always fainter than the primary. And each reflection flips the order of the light paths, so the colors end up in reversed order. Violet on the outside, red on the inside, the opposite of the primary bow. The extra reflection also sends the light out at a wider angle, about 51 degrees from the anti-solar point, which is why the secondary bow sits above the primary. Between the two bows, there's a band of sky that's noticeably darker than the sky above or below. If you've never noticed this, look for it next time you see a double rainbow. The contrast can be quite striking. This dark band is called Alexander's dark band, named after Alexander of Aphrodisias, who first described it in the 3rd century AD, making it one of the oldest documented observations in atmospheric optics. It's dark because no light from first-order or second-order rainbow reflections reaches your eyes from that angular zone. Light from single bounce reflections concentrates below 42 degrees. Light from double bounce reflections concentrates above 51 degrees. The region in between receives no concentrated rainbow light, only the dimmer light from higher-order reflections and diffuse scattering, so it appears visibly darker than the sky above and below. In principle, there are also 3rd, 4th, 5th and higher-order rainbows, produced by light that bounces 3, 4, 5 times inside the raindrop before escaping. But each additional bounce loses more light, and the higher-order bows appear at angles that place them near or around the sun, where they're washed out by the sun's own glare. The first confirmed photographs of 3rd and 4th-order rainbows appeared only around 2011, after careful image processing removed the solar glare. They're there. They've always been there. The physics guarantees it. But they're so faint and so close to the sun that they eluded detection for centuries. And here's a detail that I think is worth pausing on because it connects the rainbow to everything else we're going to talk about tonight. The rainbow works because different colors of light bend by different amounts when they pass through water. That property, dispersion, isn't unique to water. It happens in glass, in diamond, in any transparent material.
And the fact that it happens, the fact that violet light bends more than red light, tells you something deep about the way light interacts with matter. The amount by which a material bends light is described by its refractive index, a single number that captures how much slower light travels in that material compared to a vacuum. Water has a refractive index of about 1.33. Crown glass is about 1.52. Diamond is 2.42. And for most materials, the refractive index isn't actually a single number. It varies with wavelength. It's slightly higher for shorter wavelengths like violet, and slightly lower for longer wavelengths like red. That variation is dispersion, and it arises because the electrons in the material respond differently to light of different frequencies, absorbing and re-emitting photons with slightly different delays, which changes the effective speed of light through the material by a tiny, wavelength-dependent amount. Newton proved dispersion existed by separating white light with a prism. The rainbow demonstrates it on a grand atmospheric scale
every time the sun comes out after a storm. And this property of materials, this wavelength-dependent bending, would go on to become one of the most important tools in all of science. Because it's the basis of spectroscopy, the technique that allows us to identify the chemical composition of anything, including stars billions of light years away, just by looking at how they separate light into its component colors. The connection between the rainbow and spectroscopy isn't metaphorical. It's direct. In the early 1800s, a Bavarian lensmaker named Joseph von Fraunhofer was trying to manufacture the best possible optical glass for telescope and surveying instrument lenses. To test the quality of his glass, he needed a precise way to measure its refractive index at specific wavelengths. So he built the finest prism spectrometers of his era and used them to examine sunlight in unprecedented detail. And what he found was unexpected. The solar spectrum wasn't a smooth, continuous rainbow. It was crossed by hundreds of dark lines, narrow gaps where specific wavelengths were missing or dramatically reduced in intensity. Fraunhofer catalogued several hundred of these lines, assigning letters to the most prominent ones. The D lines, a pair of closely spaced dark lines in the yellow part of the spectrum, the C line in the red, the F line in the blue. He had no idea what caused them. He just needed them as reference markers for his glass measurements. But decades later, Gustav Kirchhoff and Robert Bunsen in Heidelberg figured out that each dark line corresponded to a specific chemical element in the sun's atmosphere. Sodium produces the D lines. Hydrogen produces the C and F lines. Iron produces hundreds of lines throughout the spectrum.
Every element has its own unique fingerprint of spectral lines, as distinctive as a barcode, and by reading those lines in the light from a star, you can determine what the star is made of without ever visiting it. Fraunhofer's dark lines in the solar spectrum, noticed because a glassmaker wanted to test his lenses, became the Rosetta Stone of astrophysics. Every star's composition, temperature, motion, and magnetic field can be read from its spectrum. The expansion of the universe was discovered through the redshift of spectral lines in the light from distant galaxies. The chemical composition of interstellar gas clouds, of planetary atmospheres, of the early universe itself, all decoded from the way matter absorbs and emits light at specific wavelengths. And it all connects back to dispersion, to the simple fact that different wavelengths bend by different amounts, the same fact that paints a rainbow in the sky after a summer storm.
But I want to stay with deceptions for now, because the rainbow raises a question that goes deeper than geometry. The rainbow works because different colors bend by different amounts, and that fact, dispersion, opens up a much bigger mystery. Because if materials bend different wavelengths differently, and if materials scatter and absorb and transmit light depending on wavelength, then every color you see, every single one, is a consequence of how light interacts with matter. The blue sky, the green grass, the red sunset, the white cloud. All of them are stories about that interaction. And the simplest of those stories, the one you probably never thought to question, is the most pervasive optical deception on Earth. You've probably looked up at a clear sky today and thought, without thinking, that the sky is blue. And it is, in the sense that blue light is genuinely reaching your eyes from every part of the sky. But the sky itself, the atmosphere, has no color. It's a transparent gas. If you could somehow see the atmosphere from outside, it would be essentially invisible, a thin, clear shell around the planet. The blue you see isn't a property of the air. It's a property of how light interacts with the air. And the person who finally explained why is someone whose name you might not recognize, even though you use the fruits of his work every time you notice the color of the sky. John William Strutt was born in 1842 into a family of English aristocrats. He would eventually become the third Baron Rayleigh, a title that came with a large estate in Essex and the kind of quiet, comfortable life that either breeds complacency or, in rare cases, gives someone the freedom to think deeply about whatever catches their attention. Rayleigh was the second kind. He was a physicist of extraordinary range, working on problems in acoustics, optics, fluid dynamics, and the theory of gases. He won the Nobel Prize in Physics in 1904 for discovering argon, an entire element that had been hiding in plain sight in the atmosphere. But the work that concerns us tonight, the work that explains why the sky is blue, came much earlier, in the 1870s. And it has to do with what happens when light encounters objects much smaller than its own wavelength. Here's the setup. Sunlight enters the Earth's atmosphere. The atmosphere is made of gas molecules, mostly nitrogen and oxygen, and these molecules are incredibly small. A nitrogen molecule is roughly 3/10 of a nanometer across. Visible light has wavelengths between about 400 nanometers for violet and 700 nanometers for red. So the molecules in the air are roughly 1,000 times smaller than the wavelength of the light passing through. When a wave of light encounters a particle much smaller than its wavelength, something interesting happens. The electric field of the light wave drives the electrons in the particle to oscillate, vibrating back and forth at the same frequency as the incoming light. And an oscillating charge radiates electromagnetic energy. The particle absorbs the light and then re-emits it, scattering it in all directions. This is called Rayleigh scattering, and the crucial detail, the one that explains everything, is how the efficiency of this scattering depends on wavelength. Rayleigh worked out the mathematics and found that the intensity of scattered light is inversely proportional to the fourth power of the wavelength. That's a very strong dependence. It means that if you compare blue light with a wavelength of roughly 450 nanometers to red light with a wavelength of roughly 650 nanometers, the ratio of their scattering intensities is 650 divided by 450 raised to the fourth power. That works out to about 4.3.
Blue light is scattered more than 4 times as intensely as red light. So when sunlight enters the atmosphere, the blue and violet components get scattered much more strongly than the red and orange components. The longer wavelengths pass through relatively undisturbed, continuing on their straight paths from the sun. But the shorter wavelengths bounce off molecule after molecule, scattering in every direction, filling the entire sky with a diffuse blue glow. You might wonder why the sky isn't violet, since violet light has an even shorter wavelength and should be scattered even more strongly than blue. And there are 2 reasons. First, the sun emits somewhat less violet light than blue light, so there's simply less violet to scatter. And second, the sensitivity of the human eye drops off sharply at the violet end of the spectrum. Your cone cells are much more responsive to blue than to violet. So even though violet light is being scattered more intensely, your eyes perceive the sky as blue, because that's where the overlap between scattering intensity and visual sensitivity is greatest. Now, here's where the story gets richer. If the sky is blue because blue light scatters more, what happens when sunlight has to travel through a very long stretch of atmosphere? Think about sunset. When the sun is near the horizon, its light enters the atmosphere at a very shallow angle and has to pass through a much greater thickness of air
to reach your eyes compared to when it's overhead. Much more air means much more scattering. And because blue light scatters the most, the blue is the first thing to be removed. By the time the sunlight has travelled through that long atmospheric path, most of the blue and violet has been scattered away in other directions, and what's left is the longer wavelengths, orange and red. That's why sunsets are red. The same mechanism that makes the sky blue, when given a longer path to work over, strips the blue away entirely and leaves only the warm glow of the long wavelength remnants. And think about what this means from the perspective of someone watching the sunset. You're seeing the light that wasn't scattered. The reddish glow of the setting sun is the unscattered residue. Meanwhile, someone standing between you and the sun, looking up at the sky overhead, sees the scattered light, blue and violet, bouncing down from above. The sky above them is blue, precisely because that blue was stolen from the sunlight heading toward you. One person's blue sky is another person's red sunset. They're complementary, two sides of the same scattering process. And there's an additional dimension to this story that connects to something practical. The inverse fourth power dependence means that scattering becomes dramatically weaker at longer wavelengths. Infrared light, with wavelengths 2 or 3 times longer than visible light, scatters far less than visible light. And this is why infrared telescopes can see through dust clouds that are opaque to visible light telescopes. The dust particles scatter and absorb short wavelength visible light, but the longer infrared wavelengths slip through relatively unimpeded. Some of the most spectacular images from the James Webb Space Telescope, which observes primarily in the infrared, show star-forming regions and galaxy cores that are completely hidden behind veils of dust in visible light. The dust hasn't moved. The light has simply found a longer wavelength route around the scattering. Rayleigh scattering also explains why distant mountains often appear blue or purple. The light reflecting off the mountains is white or green, but as it travels through miles of atmosphere to reach your eyes, the shorter wavelengths of the intervening air's own scattered light mix in, adding a bluish haze.
The mountains haven't changed colour. The air between you and the mountains has injected its own blue into the view. And there's another deception hiding here, one that's subtler but equally important. Rayleigh scattering is the reason that the sky is polarized. When light scatters off a small particle, the scattered light tends to be polarized, meaning its electric field vibrates preferentially in one direction rather than all directions equally. If you look at the sky at 90 degrees from the sun and view it through a polarizing filter, you can see the effect clearly. The sky gets dramatically darker or brighter as you rotate the filter, because the scattered light is strongly polarized. Bees can detect this polarization. They use the polarization pattern of the sky as a navigation compass, orienting themselves relative to the sun, even when the sun is hidden behind clouds. The sky's deception, its false blue color, has become a functional tool for an entirely different species.
So the blue sky is a lie. A beautiful, pervasive, planet-wide lie, told by the interaction of sunlight with the molecules of the atmosphere. And the explanation, Rayleigh's inverse fourth power law, connects that lie to some of the deepest physics of how light interacts with matter. Wherever charged particles are smaller than the wavelength of light, Rayleigh scattering operates. It's why cigarette smoke looks blue when seen against a dark background, and yellowish when seen with light behind it. It's why milk looks white. Fat globules of just the right size scatter all wavelengths roughly equally. And it's one of the reasons that the cosmic microwave background radiation, the afterglow of the Big Bang, can be measured at all. Understanding how light scatters off particles of different sizes is essential for separating the primordial signal from the foreground noise of our own galaxy. And Rayleigh scattering isn't the only type of scattering that shapes what you see. When particles in the atmosphere are comparable in size to the wavelength of light, like water droplets in a cloud or fog, the scattering behaves differently. It follows a more complex theory worked out by Gustav Mire in 1908, and Mire scattering is much less wavelength dependent than Rayleigh scattering. It scatters all colors roughly equally, which is why clouds are white. The water droplets in a cloud are large enough that red and blue and green light all scatter with similar intensity, and the combination of all wavelengths scattered equally is, of course, white. Fog is the same. Milk is the same. Any suspension of particles that are comparable to or larger than the wavelength of light will scatter all colors roughly equally and appear white or gray. The transition from Rayleigh scattering to Mire scattering, from blue to white, depends on particle size, and you can actually see this transition in cigarette smoke. The smoke rising directly from the tip of a burning cigarette consists of very small particles, smaller than the wavelength of light, and it scatters blue preferentially, giving it a bluish tinge when viewed against a dark background. But exhaled smoke has passed through the lungs, where the particles have absorbed moisture and grown larger, into the Mire scattering regime, and it appears whitish-grey. But the sky's false blue is just one kind of optical deception based on scattering. There's another kind, one that produces colors that are in some ways even more astonishing, because they have nothing to do with pigments, nothing to do with absorption, nothing to do with the chemical composition of the thing you're looking at. These are colors that arise purely from the geometry of surfaces and layers, colors that exist only because of the wave nature of light, exploiting the phenomenon of interference. Waves adding together and cancelling each other out. You've seen these colors. You've seen them on soap bubbles. You've seen them on oil slicks, floating on puddles. You've seen them on the wings of certain butterflies and the feathers of peacocks. And the thing about these colors is that they're arguably the most beautiful deception of all, because they're colors that shouldn't exist. The materials producing them are often completely transparent or colorless on their own. The color comes entirely from the structure, from the way incredibly thin layers manipulate light through constructive and destructive interference. And the story of how we figured that out involves, of all people, Isaac Newton, the man who championed the particle theory of light, accidentally providing some of the best evidence for the wave theory he opposed. Let's start with something you can try right now, if you have a bottle of dish soap and a wire loop nearby. Though, honestly, it works just as well as a thought experiment. Dip a loop of wire into soapy water and pull it out. A thin film of soap stretches across the loop. Hold it up so that light from a lamp or window falls on it and watch. You'll see swirling, shifting bands of vivid color moving across the surface of the film. Blues, greens, magentas, golds, all flowing and rearranging as the film thins and shifts under gravity. These colours are not in the soap. Soap is colourless. The water is colourless. The film itself, if you could somehow hold it flat and perfectly uniform, would look essentially transparent. The colours arise from something happening to the light at the film, and what's happening is interference. Here's the mechanism. When light hits the front surface of the soap film, a small fraction of it reflects. The rest passes through the thin layer of soap and water, hits the back surface, and a fraction of that reflects too. Now you have two reflected beams of light coming back at you from roughly the same spot, one from the front surface and one from the back surface of the film.
These two beams have travelled slightly different distances. The one that reflected off the back surface had to travel through the thickness of the film twice, once going in and once coming back out. That extra distance means the two beams are slightly out of step with each other. They're out of phase. If the extra distance happens to be exactly one wavelength, or two wavelengths, or any whole number of wavelengths, the two beams arrive back in sync. Peak lines up with peak, trough with trough. They reinforce each other. The reflected light at that wavelength is bright. That's constructive interference. But if the extra distance is half a wavelength, or 1.5 wavelengths, or any odd number of half wavelengths, the two beams arrive exactly out of sync. Peak meets trough. They cancel each other. The reflected light at that wavelength disappears. That's destructive interference. And here's the key. The amount of extra distance depends on the thickness of the film. So for a given film thickness, some wavelengths interfere constructively and are brightly reflected, while other wavelengths interfere destructively and are suppressed. What you see is the color corresponding to whichever wavelengths survive the interference. Change the thickness, and different wavelengths win the competition. Different colors appear. That's why a soap bubble shows a constantly shifting pattern of colors. The film is extremely thin, just a few hundred nanometers in most places, and gravity is pulling the soap downward, making the film thinner at the top and thicker at the bottom. Each point on the film has a slightly different thickness, and each thickness favors a slightly different set of wavelengths. The swirling colors are a map of the film's thickness, painted by interference. And you can see the same thing on oil slicks in parking lots. A thin layer of oil floating on water creates the same two-surface reflection, the same path length difference, the same interference. The psychedelic swirls of color on a rain puddle with a gasoline film are identical in origin to the colors on a soap bubble. Thin film interference. Now here's the wonderful irony. The person who first studied these colors systematically, who first described the precise relationship between film thickness and color, who first observed the beautiful concentric rings of color that form when a slightly curved glass surface rests on a flat one, was Isaac Newton. In his book Optics, published in 1704, Newton described what we now call Newton's rings, a pattern of alternating bright and dark circles visible when a convex lens is placed on a flat glass surface and illuminated from above. The thin air gap between the lens and the flat glass varies in thickness from 0 at the center, where they touch, to larger values farther out. And each ring corresponds to a particular air gap thickness, where the interference between light reflected from the bottom of the lens and light reflected from the top of the flat glass is either constructive or destructive. Newton measured these rings with extraordinary care. He catalogued which colors appeared at which thicknesses. He even correctly identified the mathematical pattern that the radii of the rings follow a square root progression, implying that the thickness of the air gap increases linearly with distance from the center. It was meticulous experimental work,
and it provided exactly the kind of data that a wave theorist would have used to calculate the wavelength of light. But Newton didn't do that. He couldn't, because he believed light was made of particles. Particles don't interfere. They don't have wavelengths.
So Newton came up with an alternative explanation, involving what he called fits of easy reflection and easy transmission, a mysterious oscillatory property that he attributed to his light corpuscles. The idea was that particles of light somehow alternated between a state where they were inclined to reflect and a state where they were inclined to transmit. And this alternation had a regular periodicity that depended on the color. It was, in hindsight, an awkward and unconvincing theory. Newton was essentially describing wave interference using particle language, bending over backward to avoid admitting that light behaved like a wave. Thomas Young, who came along a century later, immediately recognized Newton's rings as a textbook demonstration of wave interference. The dark rings appeared where the air gap was a half wavelength, or 3 half wavelengths, or 5 half wavelengths thick, causing the two reflected beams to arrive out of phase and cancel. The bright rings appeared where the gap was a whole number of wavelengths, so the beams arrived in phase and reinforced. Young even used Newton's own meticulous thickness measurements to calculate the wavelengths of different colors of light for the first time. He matched the known air gap thickness at each ring to the corresponding color and worked backward to the wavelength. He got values that are remarkably close to the modern numbers. Red light around 700 nanometers, violet around 400, with the other colors falling in between in the correct order. All derived from Newton's data, interpreted through the framework of wave theory that Newton himself had rejected. Newton had done the measurements. Young had the theory. And together, across a gap of 100 years, the two men's work combined to reveal the wavelength of light for the first time in human history. There's something deeply satisfying about that.
The man who fought hardest against the wave theory of light had, in his careful experiments with thin film colors, provided some of the best evidence in its favor. Newton's data was impeccable. His interpretation was wrong. And the correction, when it came, didn't diminish his contribution, but completed it, turning careful measurements without a framework into careful measurements with one. Science works like that sometimes. The person who gathers the data and the person who understands it are often not the same person, and the gap between them can span generations. Now, thin film interference might seem like a curiosity, something relevant to soap bubbles and oil slicks, but not much else. And for a long time, that's how it was treated. But beginning in the 20th century, engineers realized that thin film interference was more than a pretty trick. It was a tool, a powerful, precise, controllable tool for managing how light reflects and transmits through optical surfaces.
And the first and most important application was something so basic, so fundamental to modern optics, that you'd be hard-pressed to find a serious camera, telescope, microscope, or pair of glasses that doesn't use it. Anti-reflection coatings. Here's the problem they solve. Whenever light passes from one material to another, a fraction of it reflects off the boundary. Go from air into glass, and you lose about 4% of the light to reflection. Sounds small, and for a single surface, it is. But think about a camera lens with 6 or 8 glass elements. Each element has 2 surfaces. That's 12 to 16 surfaces. If each one reflects 4% of the light, the losses add up fast.
And what's worse, the reflected light doesn't just vanish. It bounces around inside the lens, hitting other surfaces, creating faint secondary images, reducing contrast, washing out the picture with a diffuse glow called flare.
Any photographer who has tried to shoot into the sun with an uncoated lens knows the result. A foggy, low-contrast image with ghostly bright spots. The solution is to coat each glass surface with a thin layer of a material whose refractive index is between that of air and that of glass. If you choose the right material and make the layer exactly 1/4 of a wavelength thick, something elegant happens. Light reflecting off the top of the coating and light reflecting off the bottom of the coating where it meets the glass interfere destructively. They cancel each other out. The reflection vanishes, or at least drops to nearly zero for the specific wavelength the coating is designed for. One layer can eliminate reflection for a single wavelength. Multiple layers, each with carefully chosen thicknesses and refractive indices, can suppress reflection across a broad range of wavelengths.
Modern multi-layer coatings, sometimes with dozens of individual layers, each just tens of nanometers thick, can reduce surface reflections to a fraction of a percent across the entire visible spectrum. That purplish or greenish sheen you see on the front element of a good camera lens? That's the residual reflection from the anti-reflection coating, the tiny sliver of wavelengths that the coating doesn't perfectly suppress. The coating is working precisely because of thin film interference, the same physics that creates the colors on a soap bubble, engineered and controlled with nanometer precision. And anti-reflection coatings aren't just about cameras. They're on your eyeglasses, reducing annoying reflections and making the lenses more transparent. They're on the glass covers of solar panels, maximizing the amount of sunlight that gets through to the photovoltaic cells. They're on the mirrors inside lasers, and on the lenses of projectors, and on the windows of aircraft cockpits.
Any time you need light to pass through a surface without losing intensity to reflection, thin film interference is the tool you reach for. But coatings can do the opposite too. Instead of suppressing reflection, you can design a coating that maximizes it. A dielectric mirror, sometimes called a Bragg mirror, is made of alternating layers of high-index and low-index materials, each one a 1/4 wavelength thick. Every boundary between layers reflects a small amount of light. And because the layers are spaced so that all these tiny reflections interfere constructively, they add up. A stack of 20 or 30 such layers can achieve reflectivities of 99.9% or higher at a specific wavelength. That's better than the best metallic mirror. And unlike a metallic mirror, which absorbs a small fraction of the light it doesn't reflect, a dielectric mirror is essentially lossless. The light either reflects or transmits. None is absorbed. These dielectric mirrors are essential components in lasers. The mirrors at each end of a laser cavity need to be as reflective as possible to bounce the light back and forth through the gain medium, building up the intensity with each pass. A tiny amount of loss per pass would prevent the laser from reaching threshold. Dielectric mirrors, built from stacks of thin films exploiting interference, are what make it possible. And they're designed by computing exactly how dozens of layers with precisely controlled thicknesses and refractive indices will interact with light wave by wave, reflection by reflection, interference by interference. It's soap bubble physics elevated to a high art. But nature got there first. Long before humans figured out thin film interference and started designing anti-reflection coatings, nature was producing structural colors through interference in biological systems.
and some of the most spectacular examples are on the wings of butterflies. The morpho butterfly, found in the rainforests of Central and South America, has wings of an almost impossibly vivid blue. The blue is so intense, so deeply saturated that it seems to glow. And if you look at a morpho wing under a microscope, you find something surprising. There's no blue pigment. The wing scales themselves are made of chitin, a transparent, colorless organic material. The blue is entirely structural. Each scale has a surface covered with a complex arrangement of ridges, and each ridge is made up of alternating layers of chitin and air, like a tiny stack of transparent shelves. The spacing of these layers is tuned to the wavelength of blue light. Blue wavelengths interfere constructively and are reflected brilliantly. Other wavelengths interfere destructively and pass through or are absorbed by a dark pigment layer underneath.
Change the angle at which you look at a morpho wing, and the color shifts slightly, because the effective thickness of the layers changes with viewing angle. But the morpho structure is complex enough, with enough variation in ridge orientation, that the blue remains remarkably stable over a wide range of angles. It's an engineered optical coating, evolved over millions of years of natural selection, performing the same physics that a thin film coating designer computes on a computer. Peacock feathers work similarly. The iridescent greens and blues and golds aren't pigments. They're structural colors, produced by thin film interference in layers of melanin and keratin on the barbules of the feathers. Tilt a peacock feather and the colors shift, because the interference conditions change with angle. That shifting, that iridescence, is the hallmark of structural color. Pigment-based colors don't change with angle.
They look the same from every direction because they work by absorbing certain wavelengths and reflecting the rest, and absorption doesn't depend on viewing angle. Structural colors shift because interference does depend on angle. It depends on the path length through the layers, which changes when you tilt the surface. And this distinction between pigment color and structural color has practical consequences that go far beyond butterflies and peacocks. Pigments fade. They degrade in sunlight. The molecules that absorb specific wavelengths gradually break down under ultraviolet exposure, which is why a red car left in the sun for years turns pink, and why old paintings lose their vibrancy. Structural colors, by contrast, don't fade because there's no molecule to degrade. The color comes from the geometry of the layers, and as long as the physical structure remains intact, the color persists. A morpho butterfly in a museum collection can retain its vivid blue for centuries after the insect died, because the chitin layers that produce the color are structurally stable. This has inspired a growing field of research into biomimetic structural color, designing materials that produce color through nanoscale structure rather than chemical pigments. Imagine paint that never fades, because its color comes from the arrangement of transparent nanoparticles rather than from dye molecules. Or fabric that changes color with stretching because the spacing between layers shifts. Or packaging that's vividly colored without any toxic pigments. These are all active areas of materials science, and they all trace back to the physics of thin film interference, the same physics that Isaac Newton catalogued with such care in his experiments with curved glass surfaces 3 centuries ago.
There's one more application of thin film interference that I want to mention, because it connects to something we talked about earlier, and because it's a particularly elegant example of deception turned into a tool. Interference filters. These are optical devices made from multiple thin film layers, sometimes dozens or even hundreds of layers, engineered so that only a very narrow band of wavelengths passes through. Everything else is reflected. The filter appears colored when you look at it, but the color is not from any dye or pigment. It's from the precisely calculated, constructive and destructive interference of light bouncing between the layers.
These filters are used everywhere in scientific instrumentation. In astronomy, they isolate specific spectral lines so that telescopes can image nebulae in the light of hydrogen alpha or oxygen 3, revealing structures invisible in white light. In fluorescence microscopy, they separate the excitation light from the emission light, allowing biologists to see glowing molecules inside living cells. In telecommunications, they separate different wavelength channels in a fiber optic cable carrying multiple data streams simultaneously. Each application depends on the same physics, controlling which wavelengths survive the gauntlet of constructive and destructive interference in a carefully designed stack of transparent layers. So here's the summary of what we've seen so far. Light bends through the atmosphere and creates mirages. Light disperses through raindrops and creates rainbows. Light scatters off molecules and creates a blue sky. And light interferes in thin films and creates colors on soap bubbles, butterfly wings, and anti-reflection coatings. Every one of these is a deception.
Light arriving at your eyes from a direction that doesn't match its source, or in a color that doesn't correspond to any pigment, or with an intensity that should be impossible given the materials involved. And every one of these deceptions, once understood, became a technology. But there's one more category of deception that I want to spend some time with, and it's arguably the most profound. Because so far, we've talked about light deceiving your eyes, arriving from the wrong direction, creating false colors, masquerading as something it's not. All of those are tricks performed by the light itself. The next deception is different. It's performed by you, by your visual system, by the extraordinary, imperfect, creative organ that sits behind each of your eyes, and the even more extraordinary processing machine in your skull that interprets the signals it receives. Because the truth is that you don't see the world as it is. You never have. You see a reconstruction, a model, a best guess assembled by your brain from fragmentary, noisy, ambiguous signals. And the gap between reality and your perception of it is where some of the most fascinating deceptions in all of optics live. But before we get there, I want to take a detour through one more physical deception, one that involves mirrors and reflection, and the surprisingly subtle physics of why you can see your face in a sheet of polished metal, but not in a sheet of paper, even though both are reflecting light at you right now. Think about a mirror for a second. You look into it and you see a perfect image of yourself. Sharp, detailed, full color, apparently located behind the surface of the glass, as if there were a room back there with a person in it who looks just like you. But there's no room behind the mirror. There's no person. There's a thin layer of aluminum or silver deposited on the back of a flat piece of glass, and when photons from a lamp bounce off your face, travel across the room, hit that metallic coating, and bounce back to your eyes, the geometry of the reflection preserves the spatial relationships of the original scene so precisely that your brain constructs a complete three-dimensional image in the space behind the mirror. An image that feels solid and real, and located at a specific distance behind the glass. That image is called a virtual image, and it's one of the fundamental concepts in optics. The light rays that reach your eyes after reflecting off the mirror appear to diverge from a point behind the mirror's surface. Your brain traces those diverging rays backward and concludes that there must be an object at that point. There isn't, of course. The rays never actually passed through the space behind the mirror. They hit the reflective surface and bounced back, but your visual system has no way to distinguish between light that genuinely came from behind the mirror and light that merely appears to have come from behind the mirror.
Both produce exactly the same pattern of rays entering your eyes. So your brain goes with the simplest interpretation. Something is back there. Now, why does a mirror produce such a clean, sharp image, while a piece of white paper, which also reflects light, doesn't? Both surfaces are reflecting a large fraction of the light that hits them. White paper reflects something like 80% of visible light. A good mirror reflects around 95%. The difference isn't in how much light they reflect. The difference is in how they reflect it. A mirror performs what's called specular reflection. The surface is smooth on a scale comparable to the wavelength of light. When a parallel beam of light hits it, all the rays bounce off at the same angle, preserving their relative positions and directions.
A bundle of rays that started out parallel stays parallel after reflection. Spatial information is preserved. The image is intact. Paper performs diffuse reflection. The surface is rough on the scale of light wavelengths, covered with tiny fibers and irregular bumps and valleys. When a beam of light hits it, each tiny facet of the surface reflects the light in a slightly different direction. The incoming parallel beam gets scattered into a broad range of outgoing angles. Spatial information is destroyed. No image forms. You see a bright, evenly lit surface, but you can't see any image in it because the reflected rays no longer carry organized spatial information. And here's what determines whether reflection is specular or diffuse: the roughness of the surface relative to the wavelength of light. If the surface irregularities are much smaller than the wavelength, the surface acts like a mirror. If they're comparable to or larger than the wavelength, the surface scatters the light diffusely. Visible light has wavelengths around 400 to 700 nanometers. So a surface needs to be smoothed to within a few tens of nanometers to act as a mirror. That's why a polished metal surface works as a mirror, but a sanded metal surface doesn't. The polishing process removes bumps and scratches until the surface is smooth at the nanometer scale. But why do metals reflect light so well in the first place? Why not glass or plastic or wood? The answer takes us into the electronic structure of materials, and it connects to one of the most fundamental distinctions in physics. In a metal, the outermost electrons of the atoms aren't bound to individual atoms. They're free to move throughout the entire material, forming what physicists call a sea of free electrons, an electron gas that can flow and respond to electric fields almost instantaneously. When a light wave hits a metal surface, the oscillating electric field of the wave drives these free electrons to oscillate in response. And those oscillating electrons, in turn, radiate their own electromagnetic wave, a reflected wave that carries almost all of the incoming light's energy back outward. The free electrons act like a wall of tiny antennas, absorbing the incoming wave and re-radiating it in the reflected direction. This is why metals are both shiny and opaque. The free electrons are so effective at absorbing and re-radiating incoming light that very little of it penetrates more than a few nanometers into the metal. The light can't get through. It either reflects or, for a small fraction, gets absorbed and converted to heat. Glass, by contrast, has no free electrons. Its electrons are tightly bound to atoms in a rigid lattice. Visible light doesn't have enough energy to excite these bound electrons to higher energy levels, so the light passes through unabsorbed. Glass is transparent precisely because it lacks the free electrons that would reflect and absorb visible light. And here's a beautiful subtlety. Whether a material is transparent or opaque depends on the wavelength of the light. Glass is transparent to visible light, but opaque to ultraviolet below a certain wavelength, because UV photons do have enough energy to excite electron transitions in the glass. Water is transparent to visible light, but absorbs infrared. The atmosphere is transparent to visible and radio waves, but absorbs most ultraviolet and infrared. Every material has its own set of transparency windows and absorption bands, determined by the energy levels of its electrons and the vibrational modes of its molecules. What looks transparent in visible light might be opaque in infrared, and vice versa. Now, I want to come back to the mirror's deception, because there's one more aspect of it that's worth dwelling on. The image you see in a mirror is laterally inverted. Left and right are swapped. If you raise your right hand, the person in the mirror raises their left hand. If you have a mole on your left cheek, the mirror shows it on the right. This is so familiar that you probably don't think about it, but the inversion isn't quite what it seems. A mirror doesn't actually swap left and right. What it does is reverse front and back. It turns you inside out along the axis perpendicular to the mirror's surface. If you're facing north into a mirror on a north wall, the mirror image is facing south. Front becomes back. The apparent left-right reversal is a consequence of this front-back reversal combined with the bilateral symmetry of the human body. If you hold up a book to a mirror, the text appears reversed because the mirror has flipped the book along the axis pointing at the mirror, and your brain interprets this as a left-right swap because that's the most intuitive explanation for text that reads backward. But this left-right swap is our interpretation, our brain's attempt to make sense of a spatial transformation that doesn't actually correspond to any physical left-right operation. The mirror doesn't know or care about left and right. It performs a simple geometric operation, reversing one spatial axis, and our brains, with their deep-seated sense of bilateral symmetry, interpret that as a lateral inversion. So even the most basic mirror, the most familiar optical device in your daily life, is performing a subtle deception, showing you a version of yourself that isn't quite accurate, that reverses your chirality, that presents a face that nobody else ever sees. The you in the mirror is not the you that the world sees, and every morning, when you check your appearance before heading out, you're looking at a deception and mistaking it for reality. But mirrors and reflections are, in the end, relatively straightforward deceptions.
The geometry is clean, the physics is well understood, and once you know the trick, you can correct for it mentally. The deceptions performed by your own visual system are far more subtle, far more pervasive, and far harder to escape because they're built into the hardware of your perception. They're part of how you see. You can't turn them off. And in many cases, you can't even detect that they're happening without careful experiment. So let's talk about the organ that makes seeing possible, the one that processes all of these optical deceptions and, in the process, adds a few of its own. Your eye is, at its core, an optical instrument, and it's worth taking a moment to appreciate just how remarkable it is as a piece of engineering, even if the engineering was done by evolution rather than by an optical designer. The front surface of the eye, the cornea, is a transparent dome of tissue with a refractive index of about 1.38.
It's the most powerful refracting element in the eye, responsible for about 2/3 of the eye's total focusing power. Behind the cornea is a chamber filled with aqueous humor, a clear, salty fluid with a refractive index close to water, about 1.34. Then comes the iris, the colored ring that acts as a variable aperture,
widening in dim light to let more photons reach the retina, and narrowing in bright light to reduce the flood and improve image sharpness by cutting down on aberrations. Behind the iris sits the crystalline lens, a remarkable structure made of transparent protein fibers, arranged in concentric layers, like the layers of an onion. The lens has a refractive index that varies smoothly from about 1.41 at its center to about 1.39 at its edges. This gradient index structure is a feature that lens designers find deeply impressive, because a gradient index lens can correct for certain aberrations that a uniform lens cannot. Nature stumbled onto a design principle, the grin lens, that human optical engineers didn't exploit systematically until the late 20th century. The lens is also flexible, at least in youth, and tiny muscles called ciliary muscles can change its shape, thickening it for close focus and letting it thin out for distance. A process called accommodation that gives the eye a continuously adjustable focal length. Behind the lens, the main chamber of the eye is filled with vitreous humor, a clear gel. And at the back, spread across the interior surface like wallpaper, is the retina, the detector. It contains about 120 million rod cells, which are sensitive to dim light but can't distinguish colors, and about 6 million cone cells, concentrated in the central region called the fovea, which provide color vision and high spatial resolution in bright light. The retina converts photons into electrical signals that travel down the optic nerve to the brain, where the real work of seeing happens. Johannes Kepler, in 1604, was the first person to correctly describe the eye as an image-forming optical system. He understood that the cornea and lens create an inverted, real image on the retina, just like a camera obscura creates an inverted image on its back wall. He even recognized that the image was upside down, and he acknowledged, with characteristic honesty, that he couldn't explain how the brain managed to flip it right side up. "I leave this to the natural philosophers," he wrote. The optical part of the problem, how light gets focused onto the retina, he solved. The neurological part, how the brain interprets that focused image, would take centuries more. But Kepler's optical analysis of the eye was revealing in ways he probably didn't anticipate, because it showed that the eye, as an optical instrument, is full of imperfections, aberrations, limitations, compromises. It's very far from a perfect optical system, and some of these imperfections create deceptions of their own. Start with the simplest issue. The eye has a limited depth of field. You can focus on something close or something far away, but not both simultaneously. The crystalline lens changes shape, thickening to focus on nearby objects and thinning for distant ones, a process called accommodation. But this range is limited, and it degrades with age as the lens stiffens. By the time most people reach their mid-40s, they need reading glasses because their lens can no longer thicken enough to focus on close-up text. The condition is called presbyopia, and it's essentially universal. It happens to everyone. The lens hasn't changed composition. It's still the same transparent protein, but the tissue has lost flexibility. The deception here is that you've spent your whole life thinking you could see clearly, and then gradually, almost imperceptibly, the clarity at short range fades, and you start holding books and menus farther and farther away until your arms aren't long enough. But accommodation is just the beginning. The eye has chromatic aberration, the same dispersion problem that plagues simple glass lenses. Different wavelengths focus at slightly different distances behind the lens. Blue light focuses closer to the lens than red light,
In a camera or a telescope, this would produce colored fringes around every object. Your eye gets away with it, mostly because the retina's central region, the fovea, is most sensitive to green and yellow wavelengths, which focus very close to the same point, and because your brain suppresses the slight bluish and reddish blurs at the edges. Your eye also has spherical aberration.
The cornea is a curved surface, and light rays passing through the edges of the cornea don't focus at exactly the same point as light rays passing through the center. In a precision optical system, you'd correct this with aspheric surfaces or additional lens elements. The eye handles it partly through the iris, which narrows in bright light and blocks the peripheral rays, effectively stopping down the aperture and reducing spherical aberration. In dim light, when the iris opens wide, aberrations get worse, which is one of the reasons things look a little fuzzier at night. And then there's the most dramatic structural limitation of all. The retina has a hole in it. Right where the optic nerve connects to the back of the eye and carries signals to the brain, there are no photoreceptor cells. No rods, no cones, nothing. It's called the blind spot, and it's in both eyes, roughly 15 degrees to the side of your central vision.
If you close one eye and look at the right spot, you can find it.
A small area of your visual field where objects simply vanish. But here's the thing. You've never noticed your blind spots in everyday life, even with one eye closed. The reason is that your brain fills them in. It takes the visual information surrounding the blind spot, extrapolates, and seamlessly patches over the gap. If the area around the blind spot is blue sky, your brain fills the spot with blue sky. If there's a pattern of stripes, your brain continues the stripes across the gap. It invents visual data to cover a hole in your retina, and it does this so smoothly and so convincingly that you have no idea it's happening. That's a deception. A deception performed not by light, but by your own nervous system. Your brain is showing you a complete, seamless visual field, and it's doing it by making things up. And this isn't a minor footnote. This is the central insight about how vision works.
Your brain doesn't passively receive an image from your eyes the way a screen receives a signal from a camera. Your brain actively constructs the visual scene, filling in gaps, smoothing over inconsistencies, making assumptions, applying prior knowledge, and presenting you with a finished product that feels like a direct, unmediated view of reality, but is, in fact, a sophisticated interpretation. Consider color perception. You see millions of distinct colors. The world appears to be painted in an essentially continuous spectrum of hues and shades. But your retina has only 3 types of color receptors, 3 types of cone cells, each sensitive to a different range of wavelengths. One type responds most to short wavelengths, roughly what we'd call blue. Another responds most to medium wavelengths, green. The third responds most to long wavelengths, red. Your entire experience of color is built from just 3 signals.
Every hue you've ever seen, every subtle shade and tint, is your brain's interpretation of the relative activation levels of these 3 cone types. The world appears to be painted in an essentially continuous spectrum of hues and shades. But your retina has only 3 types of color receptors, 3 types of cone cells, each sensitive to a different range of wavelengths. One type responds most to short wavelengths, roughly what we'd call blue. Another responds most to medium wavelengths, green. The third responds most to long wavelengths, red. Your entire experience of color is built from just 3 signals. Every hue you've ever seen, every subtle shade and tint, is your brain's interpretation of the relative activation levels of these three cone types. This has consequences that are genuinely surprising. For example, there is no wavelength of light that corresponds to the color magenta or pink or brown. These are colors that your brain invents. Magenta is what your brain sees when your red cones and your blue cones are both stimulated, but your green cones are not. There's no single wavelength of light that does this. The only way to produce this combination is to mix two wavelengths, one from the red end and one from the blue end, and leave out the middle. Magenta doesn't exist in the rainbow. It has no wavelength. It's a perceptual construction, a color that exists only in your brain's interpretation of a particular pattern of cone stimulation. Similarly, the color white, the sensation of looking at something that appears white, doesn't correspond to any particular wavelength.
White is what your brain perceives when all three cone types are stimulated roughly equally. That can happen with a broad spectrum of wavelengths, like sunlight, or with just three narrow wavelengths, one red, one green, one blue, carefully chosen to stimulate all three cone types equally. Your television and phone screen exploit this. They produce only three colors of light: red, green, and blue. By varying the intensity of each, they can trick your three-cone visual system into perceiving virtually any color, including colors like white and yellow that aren't actually present in the emitted light at all. Your screen never emits yellow photons. It emits red and green photons in the right ratio, and your brain perceives yellow. That's a deception. A deliberate, engineered deception that exploits the limitations of your visual system to create the illusion of a full color image using only three primaries.
And it works because Thomas Young, back in 1802, and later Hermann von Helmholtz in the 1850s, figured out that human color vision is trichromatic, based on three receptor types. The Young-Helmholtz trichromatic theory is the foundation of every color display technology ever built. And there's another deception hiding in the physics of vision that connects to a broader category of optical trickery: polarization. We touched on this when we talked about the polarization of the sky, but polarization as a phenomenon deserves a bit more attention because it's one of those properties of light that is completely invisible to human eyes, and yet profoundly useful once you know how to detect and exploit it. Ordinary light, the light from a lamp or the sun, is unpolarized. Its electric field vibrates in all directions perpendicular to the direction of travel, randomly switching orientation billions of times per second. But when light reflects off a flat surface like a road or a lake, the reflected light becomes partially polarized. The electric field vibrations line up preferentially in one direction, usually horizontal, parallel to the reflecting surface. That's why glare off a wet road or a calm lake is so harsh and blinding. The reflected light is concentrated in one polarization direction, making it more intense and more visually disruptive than the diffuse, unpolarized light coming from the rest of the scene. Polarized sunglasses exploit this. They contain a filter that blocks horizontally polarized light while passing vertically polarized light. The glare from the road, being predominantly horizontal, gets absorbed by the filter. The light from the rest of the scene, being unpolarized or vertically polarized, passes through relatively undiminished. The effect is dramatic. Slip on a pair of polarized sunglasses on a sunny day near water, and the glare vanishes.
The surface of the lake, which was a blinding mirror of reflected sky, suddenly becomes transparent, and you can see the rocks and fish underneath. You're seeing through a deception. The glare was masking the real scene, and the polarizing filter strips away the mask. The angle at which the polarization of reflected light is most complete, where the reflected beam is entirely polarized, is called Brewster's angle. It was described by the Scottish physicist David Brewster in 1815, and it depends on the refractive indices of the two materials at the boundary. For glass in air, Brewster's angle is about 56 degrees. For water in air, it's about 53 degrees. At this specific angle, the reflected and refracted beams are perpendicular to each other, and the reflected beam contains only the polarization component parallel to the surface.
Brewster's angle has practical applications in laser design, where windows tilted at Brewster's angle allow one polarization to pass without reflection losses, selecting a single polarization for the laser beam. Polarization is also what makes liquid crystal displays work. The screens on your laptop, your phone, your television all use liquid crystals sandwiched between polarizing filters. The liquid crystal molecules can be electrically rotated to either pass or block polarized light at each pixel, creating the patterns of bright and dark that form the image. Without polarization, LCD screens wouldn't exist. The invisible property of light that your eyes can't detect became the foundation of the display technology that billions of people stare at for hours every day. And there are optical illusions, a vast and fascinating category of visual deceptions that arise from the way your brain processes spatial information.
The Muller-Lyer illusion, where two lines of identical length appear different because of the direction of arrowheads at their ends. The Ponzo illusion, where two identical objects appear different in size because converging lines in the background suggest perspective and distance. The Hermann grid illusion, where you see dark spots at the intersections of a white grid on a black background, spots that vanish when you look directly at them. None of these are tricks of light. The light reaching your eyes is perfectly accurate. The deception is entirely in the processing, in the assumptions and shortcuts your brain uses to convert a two-dimensional retinal image into a three-dimensional understanding of the world. Your brain assumes that converging lines mean distance. It assumes that objects higher in the visual field are farther away. It assumes that shadows fall from above. It assumes that faces are convex, not concave. And when these assumptions conflict with the actual geometry of what you're looking at, the result is an illusion, a perceptual error, a moment where your brain's model of the world diverges from reality. So the deceptions of vision run deep. Light deceives your eyes with mirages and rainbows and false colors. Your eyes deceive your brain with blind spots and chromatic aberration, and a resolution that drops dramatically away from the center of your gaze. And your brain deceives you by filling in gaps, inventing colors, and applying assumptions that usually work but sometimes fail spectacularly. And yet, despite all of these deceptions, or maybe because of them, human vision is an extraordinary system. It works remarkably well across an enormous range of conditions, from starlight to sunlight, a range of intensities spanning about 10 orders of magnitude. It can detect a single photon under ideal conditions.
It can resolve details as fine as about 1 arc minute, roughly the size of a quarter, seen from 80 meters away. It can distinguish millions of colors with only 3 receptor types. And it does all of this with a wet, imperfect, organic optical system that would make a precision lens designer weep with frustration. But the story of optics has always been about pushing past the limitations of the eye, building instruments that can see what the eye cannot. And the fundamental tool for doing this, the technology that transformed human civilization more than almost any other single invention, is the lens. A piece of shaped glass that exploits the very same refraction, the very same bending of light that creates the mirage we talked about at the beginning. And the story of how we learned to shape glass into lenses.
How we went from accidentally noticing that certain crystals make things look bigger to deliberately designing optical systems of extraordinary precision is the story of humans learning to deceive light on purpose, to bend it, redirect it, focus it, and spread it out exactly where we want it, to take light's own tricks and turn them into tools. The oldest optical technology, older than the lens, older than glass, older than recorded history, is probably the mirror. A still pool of water reflects a usable image, and humans have been using polished surfaces to see their own reflections for thousands of years. Polished obsidian mirrors from Anatolia date to about 6000 BC. Polished copper mirrors from Mesopotamia and Egypt go back nearly as far. But mirrors just redirect light. They don't amplify it, they don't magnify it, they don't bring distant objects closer or make tiny objects visible.
The lens does all of those things, and its origin is murky and fascinating. Natural crystals with curved surfaces, particularly quartz and beryl, have been found at archaeological sites thousands of years old. The Nimrud lens, a piece of polished rock crystal found in the remains of an Assyrian palace in what is now Iraq, dates to roughly the 7th century BC. It's slightly convex and could have been used as a magnifying glass, though some scholars think it was simply decorative. We don't know for certain whether ancient peoples deliberately used curved crystals to magnify things, though the idea is plausible. A naturally curved piece of clear quartz held over a surface will make things look bigger. Someone must have noticed. But the deliberate, widespread use of lenses for correcting vision didn't begin until the late 13th century in Italy, and it's closely tied to the revolution in glassmaking that was happening on the island of Murano in the Venetian lagoon.
The glassmakers of Murano had developed techniques for producing extraordinarily clear glass, cristallo, by using plant-based sodium salts from samphire, rather than the impure mineral salts that produced cloudy, bubbly glass. This gave them a material transparent enough to be useful as a lens. Sometime around 1286, someone in Italy, possibly a craftsman in Florence or Venice, created the first wearable eyeglasses, convex lenses mounted in a frame that could be held in front of the eyes or perched on the nose. We don't know exactly who. The invention may have been a collaboration, or it may have been independently conceived by several people working in the thriving lens-grinding workshops of northern Italy. The earliest documentary evidence is a sermon delivered in Florence in 1306 by a friar named Giordano da Pisa, who mentioned that the art of making eyeglasses had been invented roughly 20 years earlier and praised it as one of the most useful inventions in the world. And it was. Before spectacles, presbyopia was essentially a career-ending condition for scholars, scribes, and anyone whose livelihood depended on close-up visual work. Once your eyes could no longer focus on text, your productive years in those fields were over. Spectacles extended the working life of an educated person by decades. The impact on scholarship, on the preservation and creation of knowledge, is difficult to overstate. Some historians have argued that the invention of spectacles was one of the preconditions for the Renaissance, because it kept the most experienced and knowledgeable minds productive far longer than nature intended. Now, how does a lens actually work? The physics is straightforward once you understand refraction. A convex lens is thicker in the middle than at the edges. When a beam of light passes through it, the part of the beam going through the center travels through more glass and is slowed down more than the parts of the beam going through the edges. The result is that the wavefront, which was flat when it entered the lens, becomes curved as it exits, bending inward, converging toward a point.
That point is the focal point of the lens, and its distance from the lens is the focal length. A convex lens converges light. Put a distant object on one side, and the lens forms a real inverted image on the other side at the focal point. That's how your eye works. The cornea and crystalline lens converge light from the scene in front of you and form a real inverted image on your retina. A camera works the same way, with a glass or plastic lens forming an image on a sensor or film. A concave lens does the opposite. It's thinner in the middle than at the edges, so it bends light outward, diverging it. The rays appear to spread from a virtual focal point on the same side of the lens as the incoming light. Concave lenses are used to correct nearsightedness, where the eye's own lens converges light too strongly, focusing it in front of the retina rather than on it. A concave spectacle lens diverges the light slightly before it enters the eye, compensating for the eye's excessive convergence and moving the focus back to the retinal surface. But lenses have imperfections, and those imperfections are themselves a kind of deception, a gap between the image you expect and the image you get. A simple spherical lens, one with surfaces that are sections of a sphere, doesn't focus all incoming rays to a perfect point. Rays passing through the edges of the lens get bent too much and focus closer to the lens than rays passing through the center. This is spherical aberration, and it produces a slightly blurred image, a soft haze around what should be a sharp point. Newton encountered this problem and considered it unsolvable for refracting lenses, which is one of the reasons he designed reflecting telescopes instead, using curved mirrors that could be shaped more precisely. And then there's chromatic aberration, the consequence of dispersion. A lens made of a single type of glass bends blue light more than red light, so the focal length is slightly different for each color. A white star, viewed through a simple lens, shows faint colored fringes around it, blue on one side, red on the other, because the colors don't focus at the same point. Chester Moore Hall, a British barrister and amateur optician, solved this problem in the early 1730s by combining two lenses made of different types of glass, one converging and one diverging, chosen so that their dispersions cancel while their focusing powers add up. This achromatic doublet was a breakthrough that dramatically improved the quality of refracting telescopes and eventually led to the multi-element lens designs used in modern cameras, where 6, 8, or even 15 glass elements work together to correct for multiple types of aberration simultaneously. There's also an entirely different approach to the lens, one that solved a practical problem so beautifully that it saved thousands of lives. The Fresnel lens, developed by the French physicist Augustin Jean Fresnel in the 1820s, takes a large, heavy conventional lens and collapses it, folding its curved surface into a series of concentric rings, each one angled to bend light by the correct amount. The result is a lens that's almost flat, much thinner and lighter than a conventional lens of the same diameter and focal length. Fresnel designed it for lighthouses, where the challenge was to focus the divergent light from a lamp into a powerful parallel beam visible from far out at sea. A conventional lens large enough for the job would have been enormously thick, heavy, and would have absorbed a significant fraction of the light passing through all that glass. The Fresnel lens achieved the same focusing power with a fraction of the glass, and the improvement in lighthouse range was dramatic. Before Fresnel lenses, a lighthouse might be visible from 5 or 6 miles, after 20 or more. Sailors in the 19th century owed their lives to this quiet, sickly French engineer who figured out that you could flatten a lens into a series of concentric steps and lose almost nothing in optical performance. Now, The combination of two lenses, one to gather and bend light and another to focus it for the eye, is what makes telescopes and microscopes possible. And the history of how these compound optical instruments were invented is one of those stories where an idea that seems obvious in retrospect took an astonishingly long time to occur to anyone. For over 300 years, from roughly 1286 to 1608, Europe had lenses. Good lenses. Lenses ground and polished with increasing skill by craftsmen in Italy, the Netherlands, and Germany. And yet nobody thought to put two of them together in a tube and look through the combination. When Hans Lippershey, a spectacle maker in Middelburg in the Netherlands, finally did it in 1608, the result was the spyglass, a device that magnified distant objects by a factor of 3 or so. The story, as told in the material about the telescope, is that he may have observed children in his shop playing with two lenses, one convex and one concave, and noticed that holding them at the right separation made a distant weather vane appear larger and closer.
Lippershey tried to patent the device. The Dutch government declined, reasoning that the principle was too simple and too easily replicated to warrant an exclusive patent. And that decision, ironically, is what spread the invention across Europe at lightning speed. Within a year, Galileo Galilei in Italy had heard about the spyglass, figured out the optical principle, and built his own version. Then he improved it, grinding his own lenses with greater care, pushing the magnification from 3 times to 9 times, to eventually about 30 times. And then he did something that nobody else had thought to do. He pointed it at the sky. What Galileo saw through that tube of leather and glass changed civilization. He pointed it at the moon and saw something that contradicted everything the prevailing Aristotelian philosophy held about the heavens. The moon was not a perfect, smooth, celestial sphere. It had mountains and craters and vast dark plains. Galileo, who was also a skilled artist, drew what he saw with remarkable accuracy, capturing the way shadows fell across the lunar terminator, the dividing line between light and dark. From the length of those shadows, he even estimated the height of the lunar mountains, getting values roughly comparable to the actual heights, which was an extraordinary feat of observational reasoning. He pointed the telescope at Jupiter and discovered 4 small points of light that moved from night to night, shuttling back and forth around the planet in a pattern that could only mean one thing. They were moons, orbiting Jupiter just as Earth's moon orbits Earth. He called them the Medicean stars, courting the patronage of Cosimo de' Medici, and we know them today as the Galilean moons, Io, Europa, Ganymede, and Callisto. Their existence was devastating to the geocentric model, because it proved that not everything in the heavens revolves around the Earth. Here was a planet with its own miniature system of orbiting bodies, visible to anyone with a telescope. He observed that Venus went through a complete cycle of phases, from crescent to full and back, just like the moon. In the Ptolemaic geocentric system, Venus should never appear full, because it was always supposed to be between the Earth and the Sun. But in the Copernican heliocentric model, Venus orbits the Sun, and depending on where it is in its orbit relative to the Earth, it can appear as a thin crescent when it's between us and the Sun, or as a nearly full disk when it's on the far side of the Sun. The phases of Venus matched the Copernican prediction perfectly, and when he turned the telescope to the Milky Way, that hazy band of light stretching across the sky, it dissolved into countless individual stars, far too faint and too densely packed to be resolved by the naked eye.
The galaxy was not a luminous cloud, it was a vast congregation of stars. Every one of these observations challenged the prevailing model of the cosmos, the Aristotelian view that the heavens were perfect and unchanging, with everything revolving around the Earth. The telescope revealed a universe that was messy, dynamic, and heliocentric, and it did it through a simple application of refraction. Two lenses bending light so that a distant object formed a magnified image in the observer's eye. The microscope followed a similar path, with the lens being turned inward toward the tiny, rather than outward toward the distant. Antony van Leeuwenhoek, a Dutch draper with no formal scientific training, but extraordinary patience and skill in lens grinding, produced single-lens microscopes of remarkable quality in the 1670s. Leeuwenhoek was secretive about his lens-making techniques, and even today nobody is entirely sure how he achieved such high quality. His lenses, tiny beads of glass mounted in brass plates and held right up to the eye, achieved magnifications of over 200 times with surprisingly good resolution. Some historians believe he drew thin fibers of glass in a flame and then melted the end into a perfect tiny sphere, which would act as a very short focal length lens. Whatever his method, the results were extraordinary. Through these lenses, Leeuwenhoek became the first human being to see bacteria, which he called animalcules. He saw protozoa swimming in pond water, spermatozoa, red blood cells, the banded structure of muscle fibers, the capillary circulation of blood in the tail of a tadpole. He sent letters to the Royal Society in London describing these discoveries, often with meticulous drawings, and the fellows of the society were initially skeptical. Tiny living creatures too small for the naked eye? It seemed fantastical. But when they verified his observations with their own microscopes, the skepticism turned to astonishment. An entire universe of life, invisible to the naked eye, had been there all along, revealed by a piece of curved glass smaller than a peppercorn. Leeuwenhoek is sometimes called the father of microbiology, and the title is deserved. Before him, nobody knew that microorganisms existed. The causes of infectious disease, the mechanisms of fermentation, the existence of cells themselves as the fundamental units of life, all of this was hidden behind the resolution limit of the human eye, waiting for someone with a good enough lens and enough curiosity to look. And this is where I want to pause and make a connection back to our central theme. Because the lens, the microscope, the telescope, all of these are tools of deception in a very specific sense. They deceive light into doing something it wouldn't naturally do. Light from a distant star would naturally spread out as it crosses the void, becoming fainter and fainter until no human eye could detect it. A telescope gathers that faint light with a large lens or mirror and bends it, concentrates it, forces it to converge onto a small area where a detector, or an eye, or a camera sensor can absorb it. The telescope deceives the light into behaving as if it came from a much brighter source. Similarly, a microscope takes light that has interacted with a tiny object, light that would normally spread in all directions and become unresolvable, and bends it, magnifies the angles, forces the diverging rays to converge as if they came from a much larger object. The microscope deceives your eye into seeing a magnified virtual image of something too small to resolve with naked vision. In both cases, the deception is deliberate, engineered, precise. Humans figured out how light bends when it passes through curved glass, and they used that knowledge to build tools that redirect light in ways that extend human perception beyond its natural limits. Every telescope, every microscope, every camera, every pair of glasses is an exercise in controlled optical deception. But there's one more form of deception, one more trick that humans learned to play on light that I think is the most remarkable of all. Because it doesn't just bend light or focus light or magnify light. It traps light, completely. It takes a beam of light and cages it inside a material, guiding it around corners, through walls, under oceans, for thousands of kilometers, without letting it escape.
And the physics behind it is something we've already encountered tonight. Something that started with a shimmer of false water on a hot desert highway. Remember total internal reflection?
The phenomenon where light hitting a boundary at a shallow enough angle bounces back completely, perfectly, with no loss. We met it when we talked about mirages, where the continuous bending of light through heated air can curve a ray so much that it effectively reflects. And we saw it in diamonds, where the high refractive index creates a shallow critical angle that traps light inside the stone, producing brilliance and fire. Total internal reflection is the key to one of the most important technologies of the modern world. And the road to that technology starts with a demonstration that a Victorian physicist performed in 1870, using nothing more sophisticated than a bucket of water with a hole in it. John Tyndall, an Irish physicist working at the Royal Institution in London, was giving a public lecture on the properties of light. Tyndall was a gifted science communicator, famous for his ability to make complex physics accessible and entertaining. And during this particular lecture, he demonstrated something beautiful. He took a tank of water with a small hole drilled near the bottom and allowed the water to pour out in a curved stream. Then he shone a beam of light into the tank so that it entered the water and hit the exit hole from the inside. The light entered the flowing stream of water and, because of total internal reflection at the water-air boundary, it was trapped inside the stream. As the water arced downward in a parabolic curve, the light followed it, bending with the stream, guided by the continuous total internal reflection at the surface. The audience saw the stream of water glowing, the light following the water around its curve, as if the water were a flexible light pipe. It was a striking demonstration, and Tyndall understood the physics. Total internal reflection keeps the light trapped inside the denser medium, the water, as long as the light hits the surface at a shallow enough angle. And in a smoothly curving stream, the light bounces back and forth inside, following every bend, unable to escape. This is, in principle, exactly how an optical fiber works. Replace the stream of water with a thin strand of glass, and you have a waveguide for light. The glass core has a higher refractive index than the glass cladding that surrounds it, and light traveling down the core hits the core cladding boundary at shallow angles and is totally reflected, bouncing its way along the fiber indefinitely. But turning this principle into a practical communication system took nearly a century of work, and the key challenge was one of materials purity. In 1966, Charles Kao, a Chinese-born British engineer working at Standard Telecommunication Laboratories in England, published a paper that many people thought was either brilliant or delusional, depending on their temperament. Kao argued that glass fibers could be used to transmit light over long distances for telecommunications, provided the glass was pure enough. At that time, the best optical glass available had attenuation, signal loss, of about 1,000 decibels per kilometer. That means that after just 1 kilometer, the light signal would be weaker by a factor of 10 to the power of 100. Essentially zero, completely gone. For practical communication, Kao calculated that you needed losses below about 20 decibels per kilometer. That meant the glass had to be roughly 50 times more transparent than anything in existence. Most people in the glass industry thought this was impossible. But Kao understood something crucial. The opacity of existing glass wasn't an intrinsic property of glass itself. It was a consequence of impurities. Tiny traces of iron, copper, and water molecules absorbed specific wavelengths of light as it passed through, gradually depleting the signal. If you could remove those impurities, if you could make glass of truly extraordinary purity, the intrinsic transparency of silica would allow light to travel through fibers for many kilometers with manageable losses. Kao spent years advocating for this idea, traveling the world,
visiting glass manufacturers, trying to convince skeptical engineers that ultra-pure glass was achievable. Most glass companies politely declined. Glass was already transparent enough for windows and bottles, they said. Who needed it to be 1,000 times more transparent? What would you even use it for? The telecommunications applications that seem obvious to us now were far from obvious in 1966. Copper wire worked fine for telephone calls. Microwave towers handled long-distance traffic. The idea that thin strands of glass might someday replace all of that seemed, to many practical engineers, far-fetched. But Cow was right about the physics. The impurities were the problem.
And in 1970, a team at Corning Glassworks in upstate New York proved it. Robert Maurer, Donald Keck, and Peter Schultz developed a process for making fused silica fibers using chemical vapor deposition, building up the glass layer by layer from ultra-pure chemical vapors. Silicon tetrachloride and germanium tetrachloride reacted with oxygen at high temperatures, rather than trying to purify bulk glass after the fact. By starting with gases and controlling the chemistry at a molecular level, they could exclude the iron and copper and water impurities that had been absorbing light in conventional glass. The resulting fiber had losses below 20 decibels per kilometer. To appreciate what that means, consider that 20 decibels of loss corresponds to the light being reduced to 1% of its starting intensity. So, after 1 kilometer of fiber, 1% of the light remains.
That sounds terrible until you remember that the previous best was 1,000 decibels per kilometer, which corresponds to the light being reduced to 1/10 billionth of 1/10 billionth of 1/10 billionth of 1%. Essentially zero. Going from 1,000 to 20 was a reduction in loss by a factor of 50, and it crossed the threshold from completely impractical to genuinely usable. And the technology kept improving. By the mid-1970s, fiber losses had dropped below 5 decibels per kilometer. By the 1980s, researchers found that silica glass has two particularly low loss windows, wavelength ranges where the attenuation reaches a minimum. One is around 1,300 nanometers, and the other, even lower, is around 1,550 nanometers, both in the near-infrared, far beyond what human eyes can see. At 1,550 nanometers, modern fibers achieve losses as low as about 1/5 of a decibel per kilometer. That means after 1 kilometer, about 95% of the light is still there. After 10 kilometers, about 63%. After 50 kilometers, still about 10%. You can send a signal a remarkable distance before it needs to be amplified. And the amplifiers themselves are a triumph of the same physics. Erbium-doped fiber amplifiers, developed in the late 1980s, use a length of optical fiber that has been infused with erbium ions. You pump energy into the erbium atoms with a separate laser, and when the weakened signal light passes through at 1,550 nanometers, it triggers stimulated emission from the excited erbium atoms, amplifying the signal without ever converting it to an electrical signal and back. The signal stays as light the entire way across the ocean. It enters the fiber in New York as a pulse of infrared photons, gets amplified every 30 to 50 miles by erbium-doped fiber amplifiers sitting on the ocean floor, and arrives in London still as a pulse of infrared photons. The entire transatlantic crossing happens at the speed of light, in the medium of light, using the physics of light. Cao shared the 2009 Nobel Prize in Physics for his work on fiber optic communication. The citation specifically mentioned his demonstration that ultra-pure glass could transmit light over long distances. It was one of those Nobel Prizes where the gap between the key insight and the award, 43 years, spoke to how long it took for the full impact of the idea to become undeniable. Think about that image. An ocean made of glass, and you could see the floor. That's how transparent this material is. And it has to be.
because the light signals traveling through these fibers need to travel tens or even hundreds of kilometers between amplification points. And here we have a beautiful closing of the circle. The mirage, that ancient deception of the desert, works because light bends when it passes through a medium with a gradient in its refractive index. Total internal reflection, the extreme case of that bending, is what traps light inside an optical fiber. And the optical fiber, carrying laser pulses under the Atlantic Ocean at terabit per second data rates, is the backbone of the global internet. A trick of light that fooled thirsty travelers for millennia became the technology that connects the modern world. But there's one more act of deception that I want to spend some time on. One more way that humans have learned to manipulate light in ways that seem almost magical.
Because so far, all the technologies we've talked about, lenses, mirrors, fibers, coatings, they all work by redirecting light. They bend it, reflect it, trap it, focus it. But none of them create an image from nothing. None of them conjure a three-dimensional illusion that hangs in space and can be walked around and viewed from different angles. That technology exists. It's called holography. And the story of how it was invented starts, unexpectedly, not with light at all, but with electrons. In 1947, a Hungarian-British physicist named Dennis Gabor was trying to improve the resolution of electron microscopes. Electron microscopes use beams of electrons instead of light to form images of extremely small objects, and they can achieve much higher resolution than optical microscopes because electrons have much shorter wavelengths than visible light. But in 1947, the electron optics available were imperfect. The lenses used to focus electron beams, magnetic and electrostatic fields, had significant aberrations that limited the resolution of the images. Gabor had an idea. What if, instead of trying to form a perfect image directly, you recorded the complete wavefront of the electrons after they passed through the sample, capturing not just the intensity, but also the phase, the timing of the wave oscillations. If you could record the full wavefront, you could, in principle, reconstruct the image later, mathematically or optically, and correct for the lens aberrations after the fact. The problem was that no detector can directly record phase. Photographic film, and the electron-sensitive equivalent, records only intensity, how bright the light or electron beam is at each point. Phase information, which encodes the three-dimensional structure and depth of the object, is lost. Gabor's insight was that you could capture phase information indirectly through interference. If you combined the wave scattered by the object with a known clean reference wave, the two would interfere, and the resulting interference pattern would encode both the amplitude and the phase of the object wave. This interference pattern could be recorded on film, and then, by illuminating the developed film with the same reference wave, the original object wave would be reconstructed, complete with its phase information, producing a three-dimensional image. Gabor called this technique holography, from the Greek words holos, meaning whole, and graphe, meaning writing. Whole writing. A record of the complete wave, not just its intensity but its full structure. He demonstrated the principle using visible light, since working with electron beams was more difficult, and published his results in 1948. The holograms he produced were crude, because the light sources available in the late 1940s were not coherent enough. Ordinary light from a lamp or the sun is a jumble of different wavelengths and phases. To produce a clean, high-contrast interference pattern, you need light that's monochromatic, a single wavelength, and coherent, meaning all the waves are in phase with each other, marching in lockstep. In 1948, no light source met those requirements well enough to produce a high-quality hologram. And then, in 1960, Theodore Maiman
demonstrated the first laser. And suddenly, Gabor's technique had the light source it needed. Emmett-Leith and Uris Upatnieks, working at the University of Michigan in the early 1960s, were the first to produce high-quality optical holograms using a laser. They used a helium neon laser, which produces a continuous, highly coherent beam of red light at 632.8 nanometers. And the results were startling.
When they illuminated their developed holographic plates with the laser beam, fully three-dimensional images appeared, hanging in space, with parallax, depth, and all the visual cues of a real three-dimensional object. You could shift your head and see around the edges of objects in the scene. You could focus your eyes at different depths and see different objects come into sharp focus. The hologram was recording and reproducing the complete light field from the original scene. Here's how it works in a bit more detail, because the principle is genuinely beautiful. You split a laser beam into two parts. One part, the reference beam, goes directly to the photographic plate. The other part, the object beam, is aimed at the object you want to record. Light scatters off the object in all directions, and some of that scattered light also reaches the photographic plate. At the plate, the reference beam and the object beam overlap and interfere.
Where their peaks coincide, you get bright fringes. Where a peak meets a trough, you get darkness. The result is an intricate pattern of microscopic, bright and dark fringes recorded on the film. This fringe pattern looks nothing like the original object. If you look at a holographic plate with your naked eye, it appears as a featureless grey smear, or at most, a faintly shimmering pattern of lines. The information is there, but it's encoded in the spacing and orientation and contrast of the interference fringes, not in any recognizable pictorial form. But when you illuminate the developed plate with the reference beam alone, something remarkable happens. The fringe pattern on the plate acts as a complex diffraction grating. It bends the reference beam in exactly the right way to reconstruct the original object beam, complete with all its phase and amplitude information. The light emerging from the plate diverges as if it were coming from the original object. Your eyes receive exactly the same wavefront they would have received if the object were actually there. And so you see the object, hanging in space behind the plate, fully three-dimensional, indistinguishable from the real thing. The hologram is a deception so perfect that it recreates not just an image, but an entire light field. It doesn't just show you what the object looked like from one angle, it encodes what the object looked like from every angle simultaneously, because the light from every direction is captured in the interference pattern. A photograph is a two-dimensional record of a three-dimensional scene. A hologram is a three-dimensional record. It captures the complete wave, not just the intensity. Gabor won the Nobel Prize in Physics in 1971 for inventing holography. And since then, holograms have found applications ranging from art to security to scientific measurement. The holographic security features on credit cards and banknotes are a common example. They're difficult to counterfeit because reproducing the precise interference pattern requires sophisticated optical equipment. Holographic interferometry, where you compare two holograms of the same object taken at slightly different times, can detect surface deformations of a fraction of a wavelength, making it an extraordinarily sensitive measurement tool for engineering and quality control. But perhaps the most philosophically interesting thing about holography is what it tells us about the nature of optical information. A hologram demonstrates that a two-dimensional surface can encode a complete three-dimensional scene. The interference pattern on the plate is flat, but the image it reconstructs has depth, parallax, and perspective. All the three-dimensional information is there, folded into the two-dimensional pattern, waiting to be unfolded by the reference beam. There's a detail about holography that surprises most people when they first hear it. You can break a hologram in half, and each half still contains the complete image. The image may lose some resolution and brightness, but every fragment of the holographic plate contains enough information to reconstruct the full three-dimensional scene. The reason is that every point on the plate receives light from every point on the object. The interference pattern at any given spot on the plate encodes contributions from the entire scene, recorded from the particular vantage point of that spot. So even a small fragment sees the full scene, just from a more restricted set of angles. Cut the hologram into quarters, eighths, sixteenths, and each piece still shows you the complete image, viewed through a progressively smaller window. The information is distributed across the entire plate, not concentrated in any one region. It's a fundamentally different kind of recording from a photograph, where cutting the image in half gives you half the scene. This distributed property of holographic information has inspired applications beyond traditional imaging. Holographic data storage, which has been explored since the 1960s and remains an active area of research, uses the principle that you can record multiple holograms on the same piece of material by changing the angle or wavelength of the reference beam for each recording. Each hologram occupies the full volume of the medium, and each can be read back independently by illuminating with the corresponding reference beam. The theoretical storage density is enormous, potentially hundreds of gigabytes, in a crystal the size of a sugar cube, because you're storing information in 3 dimensions, not on a flat surface. And holographic optical elements. Thin film holograms that function as lenses, mirrors, or beam splitters are finding applications in augmented reality displays. The waveguides in modern AR headsets use holographic gratings to couple light from a small projector into a transparent lens and guide it to your eye, overlaying digital information on your view of the real world. You're literally looking through a hologram and seeing the world with an added layer of illusion on top, a deception within a deception. Some physicists have suggested, and this is speculative and deep, that the universe itself might work this way. The holographic principle, proposed by Gerard 't Hooft and Leonard Susskind, suggests that all the information contained in a 3-dimensional volume of space can be encoded on the 2-dimensional boundary of that volume, like a hologram. This idea has profound implications for our understanding of black holes and quantum gravity. But its origin, its seed, lies in the optical insight that a flat interference pattern can reconstruct a 3-dimensional world. From mirages to metamaterials, from soap bubbles to space telescopes, the story of optics is a story of deception and counter-deception. Light deceives us with illusions. We decode those illusions and discover the underlying physics. And then we use that physics to deceive light right back, bending it and trapping it and shaping it to do our bidding. But there's one more chapter to this story. One more act of deception that brings us right up to the present day, to the cutting edge of optical technology. And it involves the most pervasive deception of all, the one that has limited astronomical observation since the first moment someone pointed a telescope at the sky: the atmosphere. Because the same atmosphere that creates mirages, that scatters sunlight into the blue sky, that produces red sunsets and false puddles on highways, also blurs every image that every ground-based telescope tries to capture. The atmosphere is a turbulent, churning, thermally uneven mess, and light passing through it
gets distorted in random, rapidly changing ways. Stars twinkle because atmospheric turbulence is constantly shifting and bending the light from them. Twinkle, twinkle, little star is a nursery rhyme about an optical deception, and for centuries, astronomers had no way to fix it, until someone figured out how to deceive the atmosphere right back. Here's the problem. Light from a distant star arrives at the top of the Earth's atmosphere as a perfect, flat wavefront. All the peaks and troughs of the light wave are aligned in a smooth plane, because the star is so far away that its light is essentially a plane wave by the time it reaches us. If you could capture that wavefront and focus it with a perfect telescope, you'd get a sharp, diffraction-limited image of the star, a tiny, clean point of light. But the atmosphere gets in the way. As the wavefront passes through the atmosphere, it encounters pockets of air at different temperatures, moving in different directions, with slightly different densities. Each pocket bends the light slightly, and the cumulative effect of passing through kilometers of this turbulent mess is that the originally smooth wavefront gets wrinkled. It arrives at the telescope's mirror, crumpled and distorted, like a sheet of paper that someone has crumpled and then tried to smooth out. The wrinkles change hundreds of times per second as the atmospheric turbulence evolves. When the telescope focuses this wrinkled wavefront, the resulting image is blurred. Instead of a sharp point, you get a fuzzy blob. The angular resolution of even the largest ground-based telescopes is typically limited not by the quality of their optics, but by the turbulence of the atmosphere to about 1 arc-second under good conditions. That's roughly the apparent size of a quarter, seen from about a mile away. A large telescope should, in principle, be able to resolve details 10 or 100 times finer than that. But the atmosphere smears everything out. This is why the Hubble Space Telescope, orbiting above the atmosphere, revolutionized astronomy, even though its mirror, at 2.4 meters in diameter, is modest by the standards of major ground-based telescopes. In space, there's no atmospheric distortion. The wavefronts arrive smooth, and the telescope can achieve its full diffraction-limited resolution. Images from Hubble are sharper than anything ground-based telescopes of the era could achieve, despite those ground-based telescopes having mirrors 2 or 3 times larger. But putting telescopes in space is enormously expensive and logistically complex. And there are many things you can do with a large ground-based telescope that you can't easily do with a space telescope. You can build the mirror bigger, much bigger. The current generation of extremely large telescopes, under construction now, have mirrors 25 to 39 meters in diameter. If they could achieve their full diffraction-limited resolution, they could see details on the surfaces of nearby stars, detect the atmospheres of exoplanets, and observe objects so faint that they're beyond Hubble's reach. But the atmosphere would blur all of that into mush. The solution is adaptive optics, and it's one of the most elegant technological counter-deceptions in the history of science. The basic idea was first proposed by an astronomer named Horace Babcock in 1953, but the technology to implement it didn't exist for another 3 decades. And when it was finally developed, it was done in secret by the United States military for the purpose of imaging Soviet satellites from the ground. The work was classified until the early 1990s, when the end of the Cold War led to the declassification of the technology and its transfer to the astronomical community. Here's how adaptive optics works. You measure the distortion in the incoming wavefront, and then you correct for it in real time by deforming the telescope's mirror to exactly compensate. Step 1. Measure the distortion. You need a reference source, a point of light at the top of the atmosphere whose wavefront you know should be perfectly smooth.
If the reference source is a natural star, it works well, but only if there happens to be a bright star very close to the object you want to observe, because the atmospheric distortion varies across the sky. The correction that works for one patch of sky doesn't necessarily work for a patch even a few arc-seconds away. To solve this problem, astronomers create their own reference star. They shoot a powerful laser beam straight up into the sky. At an altitude of about 55 miles up, in the mesosphere, there is a layer of sodium atoms deposited by micrometeors burning up in the atmosphere. The laser is tuned to the exact wavelength of the sodium D line, 589 nanometers, and it excites these sodium atoms, causing them to glow. The result is a small, bright, artificial star, a laser guide star, positioned at a known altitude, right next to the astronomical object you want to observe. Step 2. Analyze the wavefront. The light from the guide star passes through the same turbulent atmosphere that's distorting the light from your target object. A device called a wavefront sensor, typically a Shack-Hartman sensor, divides the incoming light into a grid of small sub-apertures and measures the local slope of the wavefront at each point. From these slope measurements, a computer reconstructs the shape of the distorted wavefront in real time. Step 3. Correct the mirror. Behind the telescope's main mirror, or at a secondary mirror in the optical path, there is a deformable mirror, a thin, flexible reflective surface with dozens or even thousands of actuators on its back surface. The computer sends signals to the actuators, pushing and pulling the mirror surface to create a shape that is the exact inverse of the measured wavefront distortion. When the distorted wavefront reflects off the deformed mirror, the distortions cancel out.
The corrected wavefront emerges smooth, and the resulting image is sharp. And all of this happens fast. The atmosphere changes on timescales of milliseconds, so the entire cycle of measurement, computation, and correction has to run hundreds of times per second. The wavefront sensor reads the distortion. The computer calculates the correction. The actuators push the mirror, and the cycle repeats continuously, all night long. It's a real-time feedback loop operating at kilohertz rates, correcting for a deception that the atmosphere has been performing since the atmosphere existed. The engineering challenges are formidable. The deformable mirror needs to be controlled with a precision of nanometers, pushed and pulled by actuators that respond in microseconds. The wavefront sensor needs to capture the state of the atmosphere in a fraction of a millisecond.
The computer needs to compute the inverse correction from hundreds or thousands of sensor measurements and translate that into actuator commands, all within a loop time of about 1 millisecond. When the first astronomical adaptive optics systems became operational in the early 1990s, they used mirrors with a few dozen actuators. Current systems use mirrors with thousands of actuators, and the next generation of extremely large telescopes will need mirrors with tens of thousands, each one adjusting independently, hundreds of times per second, to keep up with the ceaselessly shifting atmosphere. And there are subtleties. The atmospheric distortion varies not just in time but across the field of view. The turbulence at one point in the sky is slightly different from the turbulence a few arc-seconds away. A single guide star corrects only a limited patch of sky around it.
To correct a wider field, you need multiple guide stars, multiple deformable mirrors at different positions in the optical path, each correcting a different layer of atmospheric turbulence at a different altitude. This technique is called multi-conjugate adaptive optics, and it's one of the key technologies planned for the next generation of giant telescopes. The results, even with current systems, are spectacular. With adaptive optics, ground-based telescopes can now achieve angular resolutions comparable to, or even better than Hubble, despite looking through the full thickness of the atmosphere. The Keck Observatory in Hawaii, with its 10-meter mirror and adaptive optics system, can resolve details finer than Hubble in many cases.
Images of the galactic center, the supermassive black hole at the heart of the Milky Way, taken with adaptive optics at Keck and the Very Large Telescope in Chile, were so sharp and so detailed that they allowed astronomers to track the orbits of individual stars whipping around the black hole, providing some of the strongest evidence that the object is really there, and measuring its mass at about 4 million times the mass of the Sun. Andrea Ghez and Reinhard Genzel shared the 2020 Nobel Prize in Physics for this work, and it would have been impossible without adaptive optics. And the next generation of extremely large telescopes, with their 30-plus meter mirrors and advanced adaptive optics, will see details 10 times finer still. They will directly image planets around other stars, resolve the surfaces of giant stars, and peer into the earliest epochs of cosmic history with a clarity that even space telescopes can't match, simply because of the sheer size of their light-gathering mirrors. Adaptive optics is the ultimate counter-deception. The atmosphere distorts the light, and the telescope measures the distortion and undoes it exactly in real time, hundreds of times per second. Nature creates a deception, and engineering deconstructs it and reverses it faster than the eye can blink. And the laser guide star is itself a kind of optical deception. It's an artificial star, a beacon created by laser-excited sodium atoms in the upper atmosphere, placed in the sky precisely where the astronomer needs a reference source. The atmosphere looks up and sees what appears to be a star. The telescope looks down through the corrected optics and sees the universe with a clarity that was once only possible from space.
Deceptions upon deceptions, layered and countered and exploited, all in the service of seeing more clearly. I want to zoom out now and connect all of these threads, because I think the pattern is worth seeing as a whole. We started with the mirage, the oldest and most dramatic deception that light performs. A trick of atmospheric refraction that makes you see water where there's nothing but hot air. The physics behind it, Snell's law, the variation of refractive index with temperature, total internal reflection, turned out to be the same physics that makes optical fibers work. The mirage became the internet. We moved to the rainbow, an illusion with no fixed location, a personal private spectacle created by the geometry of sunlight and water droplets. Descartes worked out the geometry. Newton explained the colors through dispersion, and dispersion, the wavelength-dependent bending of light, became the basis of spectroscopy, the technique that tells us what the sun and the stars are made of, that lets us measure the expansion of the universe, that identified the chemical composition of galaxies billions of light years away. We talked about the blue sky, Rayleigh's explanation of why the atmosphere scatters short wavelengths more than long ones, and how that same scattering produces red sunsets, blue mountains, and the polarization patterns that bees use to navigate. The blue sky is a lie, but understanding it gave us tools for atmospheric science, for remote sensing, for understanding why materials look the way they do. We explored thin film interference, the physics of soap bubbles and oil slicks, of Newton's rings and butterfly wings. Colors that arise not from pigments but from the geometry of layers thinner than a wavelength of light. And that physics became anti-reflection coatings, dielectric mirrors, the optical coatings on every camera and telescope and pair of glasses, the interference filters that select specific wavelengths for scientific instruments. We looked at mirrors and reflection, at why metals shine and glass is transparent, at the virtual image that your bathroom mirror constructs behind its surface. And we noted how the mirror's lateral inversion is itself a subtle deception, showing you a version of yourself that no one else sees. We investigated the deceptions of vision itself, the blind spot, the trichromatic color system, the brain's habit of filling in gaps and making assumptions. And we saw how understanding those limitations enabled the invention of color displays, of television and smartphone screens that trick your three-cone visual system into perceiving a full palette of colors from just three primaries. We traced the history of lenses, from ancient crystals to Venetian spectacles to Galileo's telescope to Leeuwenhoek's microscope. Each of these is a tool for bending light, a deliberate deception that redirects photons in ways that extend human perception beyond its natural limits. We followed the story of optical fiber, from Tyndall's water fountain to Cow's vision of ultra-pure glass, to Corning's chemical vapor deposition breakthrough. Total internal reflection, the extreme case of the mirage, became the cage that traps light and carries it under oceans. We visited holography, Gabor's insight that you could record the complete wavefront of light through interference and reconstruct a perfect three-dimensional illusion that hangs in space. And we ended with adaptive optics, the real-time correction of atmospheric distortion using deformable mirrors and laser guide stars, the most sophisticated counter-deception in the history of astronomy. In every case, the pattern is the same. Light does something unexpected. It bends, scatters, interferes, reflects, or distorts in a way that creates an illusion, a deception, a gap between what you see and what's actually there. Someone figures out the physics behind the deception. And then, armed with that understanding, engineers find a way to exploit the very same physics, to turn the trick around, to use it deliberately, precisely, for purposes that the original phenomenon never suggested. The history of optics is a conversation between nature and human ingenuity. Nature shows us a trick. We study the trick until we understand it, and then we play it back, better, more precisely, in contexts that nature never imagined. From the shimmer of a desert mirage to the transatlantic fiber optic cable, from the blue of the sky to the coatings on the James Webb Space Telescope, from the rainbow over a wet field to the spectroscopic analysis of a star's atmosphere, from the colors on a soap bubble to the dielectric mirrors inside a laser, the principle is the same. Every deception contains a lesson, and every lesson becomes a technology. And the beautiful thing, the thing I find genuinely moving when I think about it, is that this conversation isn't finished. It's still going on right now, in laboratories and observatories and engineering workshops around the world. Someone is designing a new thin film coating to improve the efficiency of a solar cell. Someone else is optimizing an adaptive optics system for one of the new, extremely large telescopes. A materials scientist is experimenting with metamaterials, artificial structures with optical properties that don't exist in nature. Metamaterials are engineered composites, typically made of repeating units much smaller than the wavelength of light, arranged so that the collective electromagnetic response of the structure mimics a material with properties no natural substance possesses. The most dramatic example is a material with a negative refractive index, something first theorized by the Soviet physicist Victor Veselago in 1968, and first demonstrated experimentally by David Smith and his colleagues at the University of California, San Diego in 2001, initially at microwave frequencies. A negative refractive index means that light bends the wrong way when it enters the material. Instead of bending toward the normal, as Snell's law prescribes for ordinary materials, it bends away from it, crossing to the other side. The implications are mind-bending. A flat slab of negative index material acts as a lens, focusing light without any curvature. Light inside the material travels in the opposite direction from the energy flow. And in 2006, the British physicist John Pendry showed that a carefully designed shell of metamaterial could, in principle, guide light around an object the way water flows around a stone, rendering the object invisible. The light bends around the cloak and continues on the other side as if nothing were there. No reflection, no shadow, no distortion. true invisibility. Laboratory demonstrations of electromagnetic cloaking have been achieved at microwave frequencies, and partial cloaking has been demonstrated at infrared and even visible wavelengths, though only for very small objects and very limited conditions. A full invisibility cloak for visible light remains beyond current technology, limited by the difficulty of fabricating metamaterial structures at the nanometer scale required for visible wavelengths. But the physics is sound. The deception, in principle, is achievable. Light can be guided around an object so smoothly that an observer on the other side sees nothing. The object becomes invisible not by absorbing light or by reflecting it away, but by bending light around itself, a controlled, engineered mirage wrapped around a solid object. A quantum optics researcher is using squeezed states of light to push measurements past the limits that Heisenberg's uncertainty principle seems to impose, using quantum deception to see more clearly than classical physics should allow. The tricks haven't run out. There are still deceptions to discover, to decode, and to deploy. The conversation between light and human understanding continues, and every generation adds its own chapter. So as you lie there tonight, maybe drifting a little, maybe already half asleep, here's something to carry with you. The room around you is full of optical deceptions, right now, all working quietly in your favor. The anti-reflection coatings on your phone screen, ensuring that light passes through cleanly without ghostly reflections. The optical fiber carrying data through your walls, trapping laser pulses by total internal reflection. The pigments in the paint on your walls, selectively absorbing and reflecting wavelengths to produce the color you chose. The lens in any camera nearby, bending light through precisely curved glass to form a sharp image. Even the faint glow of any indicator light in the room, an LED, is a quantum mechanical device, converting electrical energy into photons through the physics of semiconductor band gaps. All of these are deceptions, tricks, manipulations of light that wouldn't exist if someone, at some point, hadn't looked at a natural optical illusion and asked why. Why does the sky look blue? Why does a soap bubble shimmer? Why does a diamond sparkle? Why does a mirage appear? Each question led to an answer. Each answer led to a technology.
And each technology became so woven into the fabric of daily life that you stopped noticing it was there. The light in this room has been bent, filtered, reflected, transmitted, scattered, absorbed, and re-emitted dozens of times on its journey from source to surface to your eyes. Every interaction follows the same physics that creates rainbows and mirages and blue skies. The same laws that deceived you this afternoon, showing you a puddle that wasn't on a hot road and painting the sky a colour it doesn't have, are the same laws that let you see clearly through your corrected lenses, that carry your messages across the world at the speed of light, that let surgeons see inside your body without making a cut, that let astronomers peer at the birth of galaxies 13 billion years old. The deceptions haven't stopped. They're still going, still playing their ancient tricks, still bending and scattering and interfering everywhere around you.
But now, after centuries of patient observation and clever engineering, the deceptions work for us. The lies of light have become the tools of civilization. And right now, as your eyes close and the room dims, the photons are still moving, still bouncing off walls, still refracting through glass, still scattering off molecules in the air, still carrying information at 300,000 kilometers per second, indifferent to whether anyone is watching. The physics doesn't sleep. The interference doesn't pause. The wavefronts keep propagating. The thin films keep shimmering. The fibers keep guiding their pulses of light under the dark ocean floors. You don't need to hold on to any of this. The names and numbers and wavelengths will be there whenever you want them. What matters is simpler than that. Light is the most familiar thing in your life, the first thing you reached for as a newborn, the thing that shows you every face you've ever loved.
And it turns out to be a trickster, a beautiful, reliable, endlessly inventive trickster that bends and shifts and shimmers and hides and reveals and deceives in ways that took the greatest minds in history centuries to understand. And understanding those deceptions didn't make them less beautiful. It made them more so. Because once you know why the sky is blue, you don't stop enjoying the blue. You enjoy it more. You see the physics inside the colour. You see the scattering, the wavelengths, the inverse fourth power. And somehow, the sky becomes more blue, not less. Because now, it's not just a colour, it's a story. A deep, old, beautiful story about how light touches matter and how matter touches back. Let that settle over you. Let the stories blur into the warmth of the room and the weight of the covers and the slow, steady rhythm of your breathing. The light will keep doing its work. The deceptions will keep playing. And tomorrow, when you step outside and see the blue sky and the shimmer of heat on a road and the rainbow of colour in a soap film on a puddle, you'll know what they are. Not mysteries, not accidents, just light, doing what light does, bending and bouncing and interfering and scattering, following rules so simple and so deep that the entire visible universe is painted by them. And somewhere out there tonight, someone is still asking why, still pointing instruments at the sky, still shining lasers through crystals, still computing interference patterns, still adding one more layer to the long, quiet conversation between human curiosity and the nature of light. Think about the arc of what we've travelled tonight. We started with things so simple that a child notices them. A shimmer on a hot road, a rainbow after rain, the blue of the sky.
And we ended with adaptive optics systems correcting atmospheric distortion hundreds of times per second, holographic waveguides overlaying digital information onto your field of view, and metamaterials bending light around objects to approach invisibility. The same physics connects all of it. Snell's law, interference, scattering, total internal reflection, dispersion, polarization. A handful of principles discovered over centuries by curious, stubborn, sometimes brilliant people, applied again and again in combinations of ever-increasing sophistication. And the people themselves, the ones who decoded these deceptions and learned to deploy them, they form their own chain, each link connected to the last. Ibn al-Haytham proved that light enters the eye, giving us the foundation. Snell and Descartes quantified refraction. Newton separated white light into its colours. Huygens proposed waves. Young proved interference. Fresnel gave us the mathematical framework. Maxwell identified light as electromagnetic waves. Rayleigh explained